Course 3 is really a story of something old and something new. Today we begin our journey in reinforcement learning with function approximation. In a way, this is totally new because we will, for the first time, discuss objective functions, gradient descent, parameterized functions, and generalization and discrimination.
But you are totally ready for it. The ideas of exploration, exploitation, value functions, policies, and many of the algorithms you've already learned about transfer in a natural way to the function approximation setting.
The beginning of Course 3 represents a significant change in perspective. We need to change our focus to learning parameterized functions. We will no longer assume we can store the values for all states in a table. In fact, we can't even guarantee we will see the same state more than once.
Instead, we will learn functions parameterized by a set of weights, like a neural network, to approximate the values. We won't be able to get this approximation perfect. That means in some states, we'll have to be okay with the value function being inaccurate. Despite this, the move to parameterize value functions is actually overall positive because of generalization. In fact, this better reflects how we learn. You generalize your predictions about how much work you'll have to do in this class based on your experience taking other classes.
The concepts will become a bit more technical. We will reason about the distribution of states our agents encounter and how that impacts the accuracy of the value function. We will compute the gradient of objective functions and derive new learning rules.
At this point in the specialization, you've learned about many things, and now we're going to learn about a bunch of new things. It's easy to get lost. Worse, you might lose sight of which algorithms are most relevant for the given task at hand.
To help with this, we've developed a course map. The idea is that you should be able to start at the top of the tree and work your way down to the algorithm that best fits your problem. Remember, this is a course map. It does not include all the algorithms in RL, just the ones we have talked about. The map is designed to summarize the algorithms in this course. It is not necessarily the best way to categorize the broader set of algorithms in RL. So use this as a mental model of the course itself.
Let's remind ourselves what we've covered in course 1 and 2 using the map. We started by assuming the agent could perfectly represent the values in a table. We did this to focus on the fundamental concepts of reinforcement learning without getting bogged down by approximation. The first RL methods we discussed use a model of the world that was given, not learned. We use dynamic programming methods to compute value functions and optimal policies from the model without ever interacting with the world. The branches of this map show all three DP algorithms we discussed.
In the next course, we covered sample-based methods. We first talked about Monte Carlo methods, which must wait until the end of an episode to make updates. We learned about 2 Monte Carlo methods for prediction and 2 for control.
After that, we introduced you to temporal difference learning. This family of algorithms allows the agent to make updates to the value function and policy on each step of the episode. Here, we learned about some of the most widely used algorithms from reinforcement learning, including Q-learning, SARSA, and expected SARSA.
We finished off Course 2 by looping back up to model-based planning methods. We studied the Dyna architecture, in which the agent learns a model while interacting with the world. For Course 3, we only need the right side of this map. We will first introduce parameterized functions and how we can use them to approximate value functions. We will talk about generalization and discrimination, as well as particular function approximators, including coarse coding and neural networks.
As before, we will start with prediction and derive new Monte Carlo and TD algorithms using ideas from supervised learning and gradient descent. And then we will talk about control algorithms for function approximation. This includes expected SARSA and Q-learning.
After that, we will totally blow your mind with a new way of formulating continuing control problems called average reward.
We will finish off Course 3 with parameterized policies. In a nutshell, we can parameterize policies just like we parameterize the value function. We will discuss how to do this in the average reward setting.
By the end of this course, you will know much of what you need to scale RL to real problems. You'll then get to use all this newfound understanding to implement a complete RL system in Course 4. So let's get to it. Hi, I'm Martha. I'm an assistant professor at the University of Alberta.
Hi, I'm Adam. I'm a research professor at the University of Alberta and a senior researcher at DeepMind.
Adam is well known for his work on predictive knowledge for reinforcement learning. Several research groups around the world are building on these ideas. I personally think it is some of the most important work in recent years and will only become more influential. He's also an impressive empiricist, a real master of designing experiments to cut to the key issues. He's constantly trying to improve scientific understanding in the RL community.
Martha's algorithm contributions to reinforcement learning are too many to list here. She has developed several new off-policy learning algorithms, new approaches to policy gradient, and dozens of impressive contributions to representation learning. She is truly one of the young rising stars in reinforcement learning. She also happens to be my most frequent co-author and my partner in life.
So how did you get into computer science?
Well, I grew up on the East Coast. In high school, I was really interested in the sciences, physics, chemistry, biology, but I couldn't really find a right fit. And so I kind of randomly took a course on computer science and programming, actually, in GW Basic. And it was really just a career-defining moment for me because I just remember the first time, implementing an if statement or a for loop, and it was just amazing to me that I could get a computer to execute a sequence of instructions for me. And so from there, there was no hope. I was always going to do computer science in college.
Okay, and then from there, why did you start working on reinforcement learning?
So for graduate studies, I moved out to Alberta, and I came out here to do parallel distributed computing. That's what I kind of focused on in my undergrad. So I had all my courses loaded up with, systems courses, and I had one more elective to fill. And so I was looking around for a course to take, and I did a very reasonable strategy. I looked at the pictures of the professors, and I picked the friendliest looking professor I could find. And yeah, that turned out to be Rich Sutton, and it was Introduction to Reinforcement Learning. And that course was amazing. It was really inspiring. It was my first introduction to artificial intelligence or machine learning of any kind. And so I remember one of the early assignments in that course, we were implementing SARSA to do a grid world. And again, it was another career-defining moment for me, just watching this agent learn to solve this maze. And all it got was this reward signal, -1 per step. And somehow it figured out this amazingly efficient path out of the maze. And again, it just amazed me, and I was hooked, and I was going to keep doing that for the rest of my life. So Martha, how did you end up doing research in machine learning and artificial intelligence?
Well, I actually started my undergrad in math. I've always thought functions and dynamical systems are beautiful. And then I just took a CS course for fun, and it really was very fun. So I just continued in both math and CS. And those two topics go really well together for AI and machine learning, actually. So and then I did some research in AI in the summertime and just continued from there. And I really just stayed in the field because over time I realized it was more than just about functions and math. It's really a community where you get to collaborate a lot and you get to make a career where you help people. So my day, I get to mentor a lot and I get to work in a big team working on hard problems, and it's really just very amazing to get to work on such interesting questions in a team. So there's probably some people who are taking this RL course because they want to do graduate studies in RL. So what's one of the most important things you learned in your graduate studies?
Well, maybe surprisingly enough, I learned a lesson that's useful across probably all the sciences and in fact just any form of research. And that's to really love coming to understand the details of things, to focus and do small problems and understand them really, really well. And that's something that I think is really applicable across a wide range of things, and it's something that I pass on to my students in my classes, and I really focus on teaching my graduate students that, and it's something that I hope to share to the people taking this specialization.
So what do you like about your job?
Well, I love doing research, but sometimes that can kind of grind you down a little bit. Like it's really long hours, the peer review process can be a little frustrating. And so in those times when you kind of step back and look at your research, it can seem kind of small and a little bit insignificant, and it's hard to see where that's going, how that's going to impact the world and make it a better place. And so in those times, you can always fall back and think about teaching and mentorship, right? Teaching is where you get to help people learn about things for the first time, to come to understand how your field works, and it's just so exciting. And you're also being part of the beginning of their careers, whether they end up in academia or industry or starting their own companies. It's just such an amazing experience to be part of that process. And throughout my week, the best day for me is always the days when my schedule's full of meetings with my students and I get to help them work on their problems and come to understand reinforcement learning better. So why do you think it's so important to work on reinforcement learning?
Well, I think the promise of RL is really big, but there are still a lot of open challenges. Machine learning has started being used much more widely, but RL has kind of only been used in a few areas. But at the same time, I think RL can have a really big impact. And I think within the next decade or so, we're going to see more control engineers actually using RL in their systems. We're really just going to see that it's a tool that can help in automated decision making really within larger engineered systems. But I think for that to really happen, we need to make some advances in RL. We need to start thinking more about how we're going to have robust algorithms and how we're going to get people to be comfortable using these algorithms. So I think alongside adoption in industry, we're going to need to be thinking about how we can improve RL algorithms so that these two things can happen together. So how about you? Why do you think RL is good to work on?
Well, naturally, I think reinforced learning is just the exact right framework to study AI and to make progress towards solving AI. But RL is also really important to me because I'm very interested in developmental learning systems. So you can think about, humans, babies playing on the floor or young animals learning about the world. I want to learn about those systems and how they work. And if you think about those systems, they learn an enormous amount in such a tiny amount of time, right? They learn how to crawl, they learn how their bodies work, they learn how to interact with their environment, manipulate objects, communicate with other agents in the world. And there's just generally, they're very competent learning systems. And they do that over like a couple weeks to a couple months, and it's just really astounding. And it feels like we have so much work to do to get close to those kind of systems. And so I really want to come to understand the algorithms and the representations that those systems might be using. And I think reinforced learning is the right lens to look at those things and to come to understand those things. So applications always kind of drive interest and excitement in the field, and we've had a few of them in games and some industrial control problems. But what do you think is going to be the next big thing in reinforcement learning?
Well, at its heart, I think RL is just a general approach to automated decision making. It's a tool that's going to help us in a lot of our engineered systems. And so I think the place we're really going to see it take off is in industrial control. In industrial control, we have experts that are really looking for ways to improve the how well their systems work. And so we're going to see it do things like reduce energy costs or save on other types of costs that we have in these industrial control systems. And in the hands of experts, we can really make these algorithms work well in the near future. So I really see it as a tool that's going to facilitate experts in their work rather than, say, doing something like replacing people or automating them away.
We discussed how we can frame value estimation as a supervised learning problem. In supervised learning, an important step is to define the objective to optimize. In this video, we will be more precise about the objective we would like to optimize. After watching this video, you will be able to understand the mean squared value error objective for policy evaluation and explain the role of the state distribution in the objective. Let's start by imagining an idealized scenario. We get a sequence of pairs of states and true values. We want to use this data to find a parameterized function that closely approximates v pi. We will do this by adjusting the weights so that the output of the function closely matches the associated value for a given state. In general, we can't expect to perfectly match the value function on all states. The function approximator we choose will limit the value functions we can represent. To make our goal precise, we need to specify some measure of how close our approximation is to the value function. Consider a linear value function approximation denoted by v hat. Here, to keep the visualization simple, the state is a single-dimensional and continuous. Let's plot our estimate of the value function. Now imagine the true value function looks like this. Clearly, our approximation of v pi is not perfect. But how far off is it? Let's define this more precisely. Let's start by defining a measure of the error between the value of a state and the approximate value. A natural choice is the squared error. That is, the squared difference between the value and our approximation. However, this is not enough to define an objective for function approximation. Making the estimate more accurate in one state will often mean making it less accurate in another state. For this reason, we need to specify how much we care about getting the value right for each state. We will call that mu of s. More about that in a second. We can now write our full objective as a sum of the squared error over the entire state space, where each state is weighted by mu. We call this objective the mean squared value error. Back to mu. What should we pick for mu of s? Remember, mu of s should tell us how much we care about each state. A natural measure is the fraction of time each state is visited under the policy. That means we want to minimize the average value error for the states we visit while following pi. The states that the policy spends more time in have a higher weight in the objective. We care less about errors in the states the policy visits less frequently. Mu of s is a probability distribution as shown on the slide. In this example, the policy spends little time at the extremes of the state space. This means, under the mean squared value error, we allow the value approximation to have higher error in those states. Now remember the purpose of defining this objective. We want to adapt our weights to make the mean squared value error as low as possible. From now on, we will call this objective VE bar. Changing the weights in one way may increase the value error, while changing them in a different way might decrease the value error. In the next lecture, we'll talk about how we can use gradient descent to incrementally adjust the weights. That brings us to the end of this video. You should now understand why policy evaluation under function approximation requires us to specify an objective. The mean squared value error is one possible objective. See you next time.
Previously, we looked at how value function estimation can be framed as supervised learning. We made this precise by specifying an objective. Now, we want to figure out how to find solutions to this objective. Today, we'll talk about a general strategy for minimizing objectives called gradient descent. In the following videos, we'll cover specific algorithms for the objectives in reinforcement learning. After watching this video, you will be able to understand the idea of gradient descent and understand that gradient descent converges to stationary points. We want to minimize the mean squared value error to make our value estimates close to the true value function. Recall that our value estimate is given by a function of the state parameterized by a set of real valued weights, W. These weights determine how the value is computed for each state. Changing the weights will modify the value estimate for many states. We have to think about how to change the weights to minimize the overall value error. To do that, we'll need a little bit of calculus. Hopefully you remember the idea of a derivative from calculus. Here we've plotted a function f with scalar parameter w. The derivative tells us how to locally change w to increase or decrease f. The sign of the derivative of f at a particular point w indicates the direction to change w to increase f. The magnitude of the derivative indicates the slope of the function f at the point w. That is, how quickly f will change as we vary w. Here, the derivative is positive. If we move w in this direction, we increase f. At this other point, the derivative is negative. It is pointing in a direction to decrease w. But this direction still indicates how to increase f. If we move w in this direction, it increases f. If we were to move it in the negative of this direction, it would decrease f. If f is parameterized by more than one variable, then w is a vector. In this case, we need to introduce the idea of a gradient to describe how f changes as the vector w changes. The gradient is a vector of partial derivatives, indicating how a local change in each component of w affects the function. Notice that the gradient has to be the same size as the weight vector. The sign of each component of the gradient specifies the direction to change the associated component of w in order to increase f. The direction is either positive or negative. The magnitude of the component specifies how quickly f changes as w moves in that direction. If the function is very steep in one dimension, the magnitude will be high. If it is very flat, the magnitude of the gradient in that dimension will be low. Regardless of the magnitude, the gradient gives the direction of steepest descent. It provides the direction to change w so that locally f is maximally increased. To give a specific example, let's derive the gradient of a linear value function. Remember, a linear value approximation is just an inner product of the weights with the feature vector for the state. The partial derivative of that with respect to a single weight is just the feature associated with that weight. Remember, the features themselves do not depend on the weights. This means the gradient of a linear value approximation is simply the feature vector for that state. Our objective is a function of the weights. For example, the mean squared value error is a function of the weights because it is a function of v hat, and v hat is a function of the weights. Our goal is to adjust the weights to make the objective small. Here we have a hypothetical plot of our objective. To keep things simple, let's say our function is parameterized by a single weight. The x-axis corresponds to this weight and the y-axis to the objective value for this weight. Because we have a single weight, this means our gradient is just a scalar derivative. If we want to decrease our objective function, we should move the weights in the direction of the negative of the gradient. This is the idea of gradient descent. Here's the gradient descent update rule that captures this intuition. We make small changes in the direction that will most reduce the objective. We use a step size parameter alpha to control how far we move, as otherwise there's a risk of stepping too far. This is because moving in this direction is only guaranteed to decrease the objective locally. By doing such updates repeatedly with a sufficiently small alpha, we will eventually converge to a stationary point where the gradient is 0. Likely this will be a local minimum. This means these weights are better than all weights in the immediate vicinity, but may not be the best possible. Other possible stationary points are local maxima and saddle points. These are unstable solutions. The stochasticity inherent in our algorithms is usually enough to prevent getting stuck at these poor stationary points. On the other hand, a local minima is stable, so even a stochastic algorithm will tend to converge there. For this reason, we usually talk about our algorithms converging to local minima. In some cases, gradient descent is guaranteed to converge to the global minimum, which is the best possible setting of the weights for the objective. For example, this is true for the mean squared value error with linear function approximation. For more complex function approximators, such as a neural network, a stationary point may not be a global minimum. Note that a global minimum does not necessarily correspond to the true value function. It is limited by our choice of function parameterization and depends on our choice of objective. Imagine a feature vector which just contains a single element that is always 1, no matter what state you are in. The approximate value function that minimizes mean squared value error would converge to the average value over all the states. This is not a very good value function. However, this is still the best we can do under that parameterization in terms of the value error objective. That's it for this video. You should now understand how gradient descent can be used to find stationary points of objectives, and that these solutions are not always globally optimal. Next time, we'll talk about how to use gradient descent specifically for RL. See you then!
TD learning is built on the idea that the agent can use its own estimate of the value function to update its predictions. We've seen TD learning in the tabular case. Today, we will describe how it works with function approximation. By the end of this video, you will be able to understand the TD update for function approximation, and outline the semi-gradient TD algorithm for value estimation. Recall the gradient Monte Carlo update equation. It updates our current value estimate to be closer to a sample of the return, GT. But we can consider using other targets instead of the return. In fact, we can replace the return in this update with any estimate of the value. Let's call this estimate UT. If UT is an unbiased estimate of the true value, then our function approximator will converge to a local optimum under the appropriate conditions. This was the case for the return. But we can also replace UT with the bootstrap target, such as the one-step TD target. This is still an estimate of the return, but in this case the estimate is biased. The TD target uses our current value estimate, which will likely not equal the true value function. Because of this, we cannot guarantee this algorithm will converge to a local minimum of the value error. The upside is that the TD target often has lower variance than the sample of the return. This means TD will tend to converge in fewer updates. The TD update is not actually a stochastic gradient descent update. To see why, we take the gradient of the error with respect to the weights for one sample. Remember UT is equal to the TD target. Using the chain rule, we get this expanded expression for the gradient of the squared error for one sample. But wait a minute, this doesn't look like the TD update. These two expressions would only be equal if the gradient of UT is equal to 0. This is not the case for TD. In TD, the target contains an estimate of the value which depends on the weights. This means the gradient of UT is not 0, as shown here. Therefore, TD is not performing gradient descent updates on the squared error. We call it a semi-gradient method. Despite this, TD converges in many of the cases we care about. We will discuss TD's convergence properties in an upcoming video. Here is the pseudocode for semi-gradient TD. It is actually very similar to the TD algorithm for the tabular setting. This algorithm does not have to wait until the end of an episode to make updates. TD performs an update on each step, unlike gradient Monte Carlo. On each step of the episode, the agent selects an action A in state S. We use the resulting reward and next state to compute the TD target and update the weights immediately. We continue in this way until we reach the terminal state, which is defined to have value 0. Then we start a new episode, and that's it. It's really not that different from tabular TD. That's it for today. You should now understand the semi-gradient TD algorithm.
In principle, we can use any kind of function approximation for reinforcement learning. Linear function approximation is an important special case. It is simple enough that we can understand it well, but it is still quite powerful in general. In fact, linear function approximation with TD has been used to build Atari agents that exceed human performance in many games. After watching this video, you will be able to derive the TD update with linear function approximation, understand that tabular TD is a special case of linear semi-gradient TD, and understand why we care about linear TD as a special case. Recall the update for semi-gradient TD. It adjusts the weights in the direction of the TD error times the gradient of the approximate value function with respect to the weights. In the linear case, the gradient of the approximate value for a state is just the feature vector for that state. So the update for semi-gradient TD would look like this. The weight is updated in the direction of the feature vector times the TD error. If a feature is large, then the corresponding weight can have a large impact on the prediction. On the other hand, if the feature is 0, then that weight has no impact on the prediction, and the gradient is therefore 0. The fixed basis, given by the expert design features, has a large impact on the update. If well designed, we can get effective value function approximation with a simple update. We already saw how linear value function approximation is a strict generalization of tabular value function approximation. We can show that linear TD is a strict generalization of both tabular TD and TD with state aggregation. Let's take a closer look at the algorithm to see this explicitly for tabular TD. Imagine we have a tabular state representation. Only one feature will be equal to 1, corresponding to the current state, and the rest will be 0. The value approximation for a state is equal to the weight associated with the current state. We can therefore think of the weight vector as just a table of values, one for each state. Here's the update for semi-gradient TD with these tabular features. In the update, the feature vector x of st selects a single weight associated with the current state. This weight is just the value estimate for the state. So this update corresponds to the tabular TD update we saw in a previous course. We can use the same analysis to show that TD with state aggregation is also a special case of linear TD. But why do we care so much about the special case of linear function approximation? Linear methods are simpler to understand and analyze mathematically. Much of the theory of TD learning is for the linear setting. We will discuss this more in the next video. In some applications, you may have access to expert knowledge to help you design good features. Perhaps you are the domain expert, or perhaps you can talk to someone who knows a lot about your application. If we can design these features well, then we can expect linear methods to learn quickly and achieve good prediction accuracy. Feature design provides one way to incorporate domain knowledge that can result in good performance in practice. That's it for today. We talked about the linear TD update, how tabular TD is a special case of linear semi-gradient TD, and why linear function approximation might be useful. See you next time! In a previous lecture, we introduced semi-gradient TD as approximate gradient descent in the mean squared value error. But this is a simplification of a more nuanced story. TD does not precisely optimize this objective. Instead, there's a different objective we can consider for semi-gradient TD with linear function approximation. In fact, linear TD provably converges to a well-understood approximation called the TD fixed point. We'll talk about this today. By the end of this video, you will be able to understand the fixed point of linear TD and describe a theoretical guarantee on the mean squared value error at the TD fixed point. Let's take a closer look at the TD update with linear function approximation. The value of a state is the inner product of the state features and the learned weight vector. To simplify the notation, we'll use xt to mean the features associated with the state st. We can then expand the TD update like this. We can rewrite this using a bit of linear algebra. First, we'll pull xt into the brackets. We then use the fact that taking the transpose of a scalar leaves it unchanged. Now let's think about what this update looks like in expectation. Understanding the expected update is key for proving convergence. The TD update can be rewritten as the expected update plus a noise term, and so is largely dominated by the behavior of the expected update. The expected update characterizes the expected change in the weight from one time step to the next. The expected TD update can be written as a vector b minus a matrix A times the current weights. The matrix A is defined in terms of an expectation over the features, while the vector b is defined in terms of the features and the reward. The weights are said to converge when this expected TD update is 0. We call this point WTD. If A is invertible, we can express this as WTD equals A inverse B. More generally, WTD is a solution to this linear system. We call this solution the TD fixed point. It can be proven that linear TD converges to this point. In fact, it can be shown that TD minimizes an objective that is based on this A and B. This objective extends the connection between TD and Bellman equations to the function approximation setting. Recall that in the tabular setting, we described TD as a sample-based method for solving the Bellman equation. Linear TD similarly approximates the solution to the Bellman equation, minimizing what is called the projected Bellman error. The details of this objective are beyond the scope of this course, but you can refer to the course textbook for more detail. The key takeaway is that even though TD does not converge to the minimum of the mean squared value error, it does converge to the minimum of a principled objective based on Bellman equations. Nonetheless, we do still want to understand the relationship between the solution found by TD and the minimum value error solution. We can formally characterize this relationship with this equation. The difference between the TD fixed point and the minimum value error solution can be large if gamma is close to 1. If gamma is very close to 0, on the other hand, the TD fixed point is very close to the minimum value error solution. This bound also depends on the quality of the features. If the features are limited, both the minimum mean squared value error and the value error at the TD fixed point may be large. If we can perfectly represent the value function, then regardless of gamma, the TD fixed point is equivalent to the minimum value error solution. This is because both the left and right-hand sides would be 0. So, in general, why isn't the TD fixed point equal to the minimum value error solution? This is because of bootstrapping under function approximation. If our estimate of the next state is persistently inaccurate due to function approximation, then TD may forever update towards an inaccurate target. On the other hand, if our function approximator is very good, then our estimate of the next state will become very accurate. So bootstrapping off this estimate is not problematic, and the error for the TD solution is close to the minimum value error. That's it for today. You should now know a bit more about why linear semi-gradient TD is guaranteed to converge to a fixed point, called the TD fixed point, and how the TD fixed point relates to the minimum mean squared value error.
This week, we learned a lot about how to extend reinforcement learning from the tabular case to function approximation. In many real-world problems, it is not practical to enumerate every possible state in a table. So moving to function approximation is a big step in making reinforcement learning more broadly applicable. In this video, we'll do a quick recap of what we've learned. We've covered a lot of material already, and it's easy to get lost in all the different concepts. So let's step back and see how this week's topics fit into the bigger picture. This map shows all the different algorithms we've covered in this specialization and how they relate to each other. Remember, the map only shows the algorithms we present in the specialization. The main conceptual change this week was moving to the framework of parameterized function approximation. This means we are no longer using a table to store the value of each state. This puts us on the left side of the map. Our discussion of average reward will come later. For now, let's focus over here. This week, we focused on the policy evaluation problem. We covered two algorithms, gradient Monte Carlo and semi-gradient TD. Gradient Monte Carlo makes updates at the end of each episode. TD bootstraps using the value estimate at the next time step, so it does not need to wait until the end of an episode to learn. Now that we've got the big picture, let's do a quick recap of some of the details. We described a parameterized value function as a mapping from states to real numbers. The output is controlled by a vector of real valued weights, W. We use the notation v hat of s and w to represent the approximate value function. This indicates that the value estimate is determined by the current state and the learned weight vector. One example of a parameterized value function is a linear function of fixed or expert design features. Another example is a neural network. We talked about two key properties of function approximation, generalization and discrimination. Updating the value of one state can improve the value estimates of other states. This generalization can make learning faster. We also want our value function to assign different values when states are very different. We call this discrimination. Next, we discussed how to use ideas from supervised learning to learn approximate value functions. We cannot guarantee perfect approximation for every state's value. So we need to define an objective, a measure of the distance between our approximation and the true values. We use the mean squared value error objective, the sum of the squared error between the value of each state and our approximate value, weighted by the visitation frequency, mu. We discussed how stochastic gradient descent can be used to optimize our objective. The gradient Monte Carlo algorithm performs stochastic gradient descent using sampled returns to update the weights. This means it can learn an approximate value from the experience generated by an agent interacting with the world. We also introduced semi-gradient TD as an approximation to stochastic gradient descent. Semi-gradient TD takes advantage of bootstrapping, and in practice may converge much faster than Monte Carlo. The semi-gradient part of the name reminds us that it is not a gradient descent algorithm. Finally, we discussed the linear semi-gradient TD algorithm, or TD with linear function approximation. Linear TD provably converges to a well-understood point. You now have a good foundation to understand reinforcement learning with parameterized functions. Next, we will discuss different ways to construct state and state action features. Until next time. The features used to construct value estimates are one of the most important parts of a reinforcement learning agent. Today, we'll discuss one simple but effective way to do this. By the end of this video, you'll be able to describe coarse coding and describe how it relates to state aggregation. Let's talk about a new way to create features for linear value functions. Recall that approximate value functions are parameterized by a weight vector w. To calculate the value of a state, we first compute the features and construct the feature vector x of s. Then the value of the state is approximated by a dot product between the weight vector and the feature vector. Recall that a tabular representation can be expressed as a binary feature vector. Each state is associated with a different feature. If the agent is in a state, then the feature corresponding to that state is 1. All other features are 0. The tabular case is just a special case of linear function approximation, where the feature vector is an indicator or one-hot encoding of the state. Of course, this is not feasible when the size of the state space becomes much larger than the agent's available memory. Suppose we want to represent the location of this fish that's swimming in a pond, a two-dimensional state. The fish can be in one of infinitely many locations. It's impossible to represent all these locations with a finite lookup table. Recall that we can use state aggregation to associate nearby states with the same feature. This is like treating all states within each square as the same state. In this example, all the groups have roughly the same shape. But it's not necessary to use the same shape. In general, we can aggregate states using any shapes we want, as long as those shapes do not have any gaps or overlap. State aggregation does not usually allow the shapes to overlap, but this restriction is not necessary. In fact, by allowing overlap, we obtain a more flexible class of feature representations called coarse coding. Let's look at an example feature vector for the fish's current location in the pond. Remember, each index in the feature vector corresponds to one of the shapes. The feature corresponding to the circle is active or set to 1 if the fish is within that circle. Otherwise, the feature is set to 0. The feature's receptive field corresponds to the locations that activate that feature. When the fish moves to a new location, it's usually covered by a different set of circles. Nearby states will have similar feature activations, but they may also have different components active, including different numbers of active features. In this example, there's always at least one active feature and at most 3 active features. All the ideas we've discussed so far are not limited to 2D state spaces. Coarse coding can also be applied to higher dimensional inputs. In this video, we talked about how the tabular case can be represented with a binary one-hot encoding of the state, and how coarse coding is a generalization of state aggregation. See you next time. We previously talked about coarse coding. Today, let's look at a computationally efficient way to perform coarse coding, tile coding. By the end of this video, you'll be able to explain how tile coding achieves both generalization and discrimination, and understand the benefits and limitations of tile coding. Tile coding is a specific type of coarse coding. Tile coding performs an exhaustive partition of the state space using overlapping grids. This is perhaps best understood through an example. Let's revisit our fish friend who lives in a two-dimensional continuous state space, the pond. Unlike coarse coding, which uses arbitrary shapes, tile coding uses squares. What's the most convenient way to lay out a bunch of squares over a space? It's a grid. Let's call this grid a tiling. So far, using this is just state aggregation. Larger tiles will result in increased generalization. Although the ideal tile size depends on the specific problem, it's generally a good idea to use larger tiles. To improve the discriminative ability of our tile coding, we can put several tilings on top of each other. Each tiling is offset by a small amount. Offsetting each layer of tiling creates many small intersections. This results in better discrimination. In practice, it is useful to use a large number of tilings. For one tiling, generalization only occurs within the square, but with multiple tilings, updates in this state generalize to these other states. The generalization in this case is diagonal. If we had used random offsets, then the generalization would be more spherical and homogeneous. This is discussed more in the textbook. Let's talk about how to control the generalization properties further. We can do this by creating a grid of rectangles rather than squares. An efficient way to do this is to scale each dimension of the state space. The environment appears to have gotten squished here. Actually, layering squares over this squished environment is like laying rectangles over the unsquished environment. By using rectangles, we can control the broadness of the generalization across each dimension of the state space. Tile coding can represent a wide range of functions, but its utility does not end there. Tile coding is also computationally efficient. Since grids are uniform, it's easy to compute which cell the current state is in. Due to its computational efficiency, tile coding can be used to quickly run preliminary experiments in low-dimensional environments. However, as the number of dimensions grows, the number of required tiles grows exponentially. As a result, it can be necessary to tile input dimensions separately. Whether or not input dimensions can be treated independently depends on the specific problem. In this video, we talked about coarse coding and how it is a generalization of state aggregation. See you next time. So far, you've learned about tile coding, but we haven't connected it back to reinforcement learning yet. Well, the wait is finally over. Today, we'll explain how to use tile coding together with linear TD. By the end of this video, you'll be able to explain how to use tile coding with temporal difference learning, and identify important properties of tile-coded representations. The number of active tiles is always significantly less than the number of total tiles. We can use this to calculate the value function efficiently. Recall that with linear function approximation, the value function is a dot product between a weight vector and a feature vector. Let's see what this dot product looks like with a sparse binary feature vector. If we were to multiply the two vectors element-wise, many of the element-wise products will be 0. This means we only have to consider the weights at the non-zero elements of the feature vector. Because the features are binary, the weights at the non-zero features are multiplied by 1. Computing the dot product in the usual way would be expensive. Instead, we can just sum the weights corresponding to the active features. Note that this takes a consistent amount of time because the number of active features is the same in every state. The feature vectors produced by tile coding make querying the value function cheap computationally. Let's look at an example value function with tile-coded features. Suppose we're back at the old pond, with 2 tilings of 4 tiles each. We've color-coded the tilings, and each tiling square is indexed as shown. If the position of the fish and the weight vector are as shown, what is the value of the fish's position? We can see the fish intersects square 1 belonging to the purple tiling and square 4 belonging to the orange tiling. This results in the following feature vector for this state. Now we simply calculate this state's value with a dot product. The feature vector is binary, so we can just add up the weights at the locations with non-zero features. This gives us a value of 2. Now let's run an experiment with tile coding and compare it to state aggregation. Recall that tile coding is effectively multiple instances of state aggregation, or tilings, layered on top of each other. Our environment is the 1000 state random walk. The states are numbered from 1 to 1000, and all episodes begin in state 500. At each time step, the agent randomly transitions to one of the 200 neighboring states on either side. Overshooting states 1 or 1000 will result in a transition to the terminal state. For example, look at the possible transitions to the left of state 2. 1 will go to state 1, and the remaining 199 will go to the terminal state. Let's talk about how we can use function approximation in this problem. We'll start with state aggregation. Let's use a state aggregation with 5 groups, each corresponding to 200 states. Now let's design a tile coder for this problem with 50 tilings. We treat the 1000 states as an interval, where each tile corresponds to 200 states. Since each tile has 200 states, you might think we only need 5 tiles to cover the full space of 1,000 states. However, each tiling is slightly shifted or offset from the others. An extra tile is needed to cover the space left uncovered. Because of this, each of our tilings contains 6 tiles rather than 5. Let's compare these two function approximators with gradient Monte Carlo. The step size parameter alpha is scaled by the number of active features, 50 for tile coding and 1 for state aggregation. Let's look at the results. We plot the value error averaged over 30 runs after each episode. Both agents learn quickly due to aggressive generalization. However, the tile-coded representation is able to better discriminate between states and achieves a lower value error. It's interesting that even though the tile coder has many more parameters, it can learn just as quickly as the core state aggregation. But it also achieves better discrimination because of the small intersections created by multiple overlapping tiles. That's it for today. In this video, we talked about how tile coding can be used to approximate value functions in policy evaluation, and we compared tile coding to state aggregation in a simple example. Next time, we're going to move beyond fixed representations and begin learning representations with neural networks.
Today, we will discuss neural networks, a flexible and powerful class of nonlinear function approximators. Reinforcement learning with neural networks has been used to create a world champion Go player, to create Atari agents capable of superhuman performance, and even to help with autonomous cars. By the end of this video, you will be able to understand feed-forward neural networks, define an activation function, and understand how a neural network is a parameterized function. Let's walk through a simple neural network. Each of these circles represents nodes in the network. Each of the lines represents connections between nodes. The nodes are organized into layers. When new data comes in, it starts in the input layer and is sent through the connections to the next layer of nodes. This layer performs some computation on the data, then sends the results to the next layer. This process continues until the last layer produces the final output. We call this a feed-forward neural network because the data always moves forward through the layers. None of the connections loop back through the network. If they did, then a node's output could influence its own input. Such a neural network is called a recurrent neural network. When data is passed through a connection, a weight is applied. The node then sums up each of its weighted inputs and applies some activation function to this sum. The activation function is often a nonlinear transformation. Common activation functions include sigmoidal functions like tanh or the logistic function, rectified linear units or ReLU, or even thresholding units. Let's take a look at how to write a feed-forward pass of a neural network mathematically. At each node, we have two vectors, the inputs and the weights for each input. The first subscript refers to the node the connection comes from. The second subscript refers to the node the connection feeds into. We dot product the weights with the input and pass the result through the activation function. Notice here that S is a row vector, so we do not need to write the dot product with the transpose. Each layer consists of many such nodes. A neural network is just a parameterized function, though this can be a bit hard to see by thinking of it as a collection of connected nodes. To see this more explicitly, let's rewrite the operations in the network using matrix vector multiplication. We can view the inputs to a layer as a row vector and the weights for that layer as a matrix. In other words, as this two-dimensional array. We can compute the output of an entire layer using matrix multiplication. We then apply our activation function to each element of the outputted vector. If this output isn't the final layer, this output vector becomes the input to the next layer, and we repeat the process. That's it for this video. We explained how neural networks consist of a network of nodes which process and pass information along, and discussed how a feed-forward neural network is a parameterized function. See you next time. Tile coding is one way to create a fixed set of features for prediction. Neural networks provide a strategy for learning a useful set of features. Today, we'll discuss how neural networks create these features. By the end of this video, you will understand how neural networks do feature construction, and you will understand how neural networks are a nonlinear function of state. Let's revisit feed-forward neural networks. When we first build the neural network, we need to specify the initial weights. The way we initialize the weights is important, but more on this later. For now, let's just assume they are drawn from some random distribution. Let's take a look at what happens to a given input vector as we pass it through the network. Let's start by looking at only one node of the network. Each of the inputs are multiplied by their corresponding weights. Then, the weighted sum of these inputs is passed to a nonlinear activation function, resulting in a nonlinear function of the inputs. This process is done again and again for each of the nodes in the layer. Each node has a different set of weights, so will produce a different output, which we call a feature. All of these new features collectively are considered the new representation. This process is actually not that different from tile coding. We pass inputs to a tile coder and get back a new representation. So, in both cases, we construct a nonlinear mapping of the inputs to produce the features. In both cases, we take a linear combination of the representation to produce the output, the approximate value of the current state. Let's get more insight into the neural network representation by contrasting with tile coding. Recall that when we created the tile coder, we had to set several parameters: the size and shape of the tiles, and the number of tilings. These parameters were fixed before learning. In a neural network, we have similar parameters corresponding to the number of layers, the number of nodes in each layer, and the activation functions. These are all typically fixed before learning. In this sense, both use prior knowledge to help in constructing features. However, in addition, the neural network also has adjustable parameters that change the features during learning. The neural network can use data to improve the features, whereas the tile coder cannot incorporate new information from data. Both tile coding and neural networks produce features that are nonlinear in the input space. We can understand this better by visualizing the hidden layer of a pre-trained neural network. We trained an agent in a continuous 2D space that contains a narrow corridor between two walls. Here, we've plotted the receptive field for an individual feature learned by the network. The axes correspond to XY locations, which is the state space of the MDP. Each point in the plot corresponds to the feature value for that XY state. Darker means larger activation. If it is white, the feature is not active for that state. So what does this plot mean? This plot shows for which state this feature is active, meaning the feature's magnitude is above a small threshold. So at a higher level, this plot shows you how this feature generalizes. Updates to its weight change the values for all these states. Looking at the receptive fields for several features, we can see that different features generalize in different ways and form complex nonlinear shapes. The activations do not have hard boundaries like in tile coding. These learned features can have boundaries that change smoothly. This feature has different degrees of generalization depending on the state. It's also kind of fun that the feature activations in this network show us the locations of the two walls. That's it for this video. You learned how neural networks can be viewed as a way to construct features, and that neural networks are nonlinear functions of state. Bye for now.
The choice of neural network architecture can have a big impact on performance. This includes the number of nodes, the activation functions, and how the nodes are arranged and connected. Today, we will provide some intuition on the role that depth can play in the network. By the end of this video, you will understand how deep neural networks are composed of many layers, and understand that depth can facilitate learning features through composition and abstraction. We can view a neural network as being a modular system where each layer is a module. We can add and remove layers, and we can change the types of layers that we use. The depth of the network is defined by the number of hidden layers in the network. In theory, a neural network need not be deep. A neural network with a single hidden layer can approximate any continuous function given that it is sufficiently wide. We call this the universal approximation property. However, practical experience and theory suggest that deep neural networks may make it easier to approximate complex functions. One reason for this is that the depth allows composition of features. Composition can produce more specialized features by combining modular components. Consider an intuitive example. The input is the raw pixels of an image. The earlier layers might learn to capture low-level features like lines at various angles. The next layer may learn to compose those lines into various shapes. From these, the network might be able to detect objects or animals in an image. This typically works better than trying to immediately infer these directly from the raw pixels. By adding more layers or more units to each layer, we can represent more complex functions. Depth can also be helpful for obtaining abstractions. Deep neural networks compose many layers of lower-level abstractions, with each successive layer contributing to increasingly abstract representations. Consider the previous example. The network might eventually represent the concept of an owl with a single bit. A 0 meaning the image does not contain an owl, and a 1 meaning the image does contain an owl. At this level, all the extra detail in the image has been removed. We no longer know the color of the owl or even what's in the background. In fact, we can explicitly design the network to remove unnecessary details from the input. For example, a network can be designed with a bottleneck layer. The idea is simple. Each successive layer contains less nodes than the layer before. The representation is the layer with the fewest nodes and contains the key details needed for prediction. Overall, depth in a network can significantly improve our agent's ability to learn features. In this video, we described how networks can be composed of multiple layers and discussed that depth facilitates composition and abstraction. Today, we discussed some of the potential benefits of deep neural networks. In practice, picking the right architecture can be difficult and can significantly impact performance. We will not discuss the network architectures further in this course. There are many good resources on this topic. Check them out if you want to know more. Next, we will discuss learning the parameters of a neural network.
The updates for our algorithms have been pretty simple, and most have been based on gradient descent. The same is true for neural networks. The backpropagation algorithm is actually not that complex. It is in fact just gradient descent. But the gradient is a bit more complex because of the nested functions. By the end of this video, you will be able to derive the gradient of a neural network and implement gradient descent on a neural network. As in linear function approximation, the first step is to define a loss on the parameters of the neural network and then derive the gradient. The loss function specifies how far the network's predictions are from being correct. Our goal in training the neural network is to find the parameters which minimize this loss function. The gradient of a function points in the direction of greatest descent. By moving in the direction opposite the gradient, we move in the direction that most quickly minimizes the loss. So how do we compute this gradient of the loss function for a neural network? Before we get started, let's establish some notation. The input to the network is S and the output is Y hat. The hidden layer is the learned features, so let's call it X. The weights A produce the features, the weights B linearly weight X to produce the output. The output of each layer of the network can be represented as a vector. Here, that is X and Y hat. The first index of the weight matrices refers to the inputs to that layer, and the second index refers to the outputs. We assume for now we have a generic loss L, so we can describe the basic idea. An example of L is the squared error. For the derivation, we will keep L generic. We will give you the specific update with the squared error later. Before we dive into the derivation, let's get oriented. Though the derivation is a bit involved, we will find that the final update is quite simple. Each matrix of parameters has an update that looks like an error term delta times the input to that layer. For A, the input is S. For B, the input is X. Further, we will find that delta A can be efficiently computed as a function of delta B. The errors delta B from the output of the network are propagated backwards to this earlier layer to help determine the role A had in producing that error. So now, how do we get delta A and delta B? For fun, and of course educational purposes, let's do the full derivation now. Let's start at the output of the network and work backwards. There's a good reason for this, as you will see. We start by taking the partial derivative of the loss function with respect to the first set of weights, b. We use the chain rule, giving the derivative of L with respect to y hat times the derivative of y hat with respect to b. The next step is again to use the chain rule for this derivative. To make this easier, let's introduce a new variable, theta. Theta is the output of the hidden layer times the last set of weights. Let's write it down on the side so we remember it. Now let's rewrite y hat using theta. Let's expand the derivative of y hat with respect to b. Using the chain rule, we get the derivative of fb with respect to theta times the derivative of theta with respect to b. The derivative of theta with respect to b is x. This is because theta is a linear function of b, and because x does not depend on b. And now we're done deriving the gradient for b. Next, we'll do the gradient for a. But before that, let's make some choices for the loss and activation so that we can see a specific instance of this general equation for b. Let's define L to be the squared error and use a linear activation on the last layer. The derivative of the loss with respect to y hat is this. The derivative of the activation for the output layer is 1. This is because fb is the identity, and the derivative of theta with respect to itself is 1. Here's the generic gradient of the loss with respect to b. Plugging this into the gradient with respect to b, we get y hat minus y times 1 times x. To ease notation while computing the gradient with respect to a, let's define a new term, delta b. We can replace most of the gradient for b so that it now becomes delta b times its input, x. Now, to compute the gradient with respect to a, we need to go through the same steps as for b. The main difference is that we have one extra chain rule step because the weights a also affect x. Let's start there. Let's expand this derivative using the chain rule. Before we expand the next term, let's introduce another helper variable, psi equals inputs s times a. Let's throw that off to the side and rewrite x to use it. We then expand the next term. Using the chain rule again, we get the derivative of fa of psi with respect to psi times the derivative of psi with respect to a. And because psi is s times a, we get that d psi dA is s. Putting it all together, we finally get the derivative with respect to a. We now have all we need to compute the gradient of the network parameters. We can clean up this derivative by again defining a term delta A. Now the derivative with respect to A is delta A times its input S. Notice that both gradients can be rewritten in a similar form. They have a term delta that contains an error signal times their input. Let's take a brief look at some pseudocode for implementing the backprop algorithm with stochastic gradient descent. For each data point, sy, in our dataset, we first get our prediction y hat from the network. This is typically called the forward pass. Then we compute the gradient starting from the output. We first compute delta b and the gradient for b. Then we use this gradient to update the parameters b with step size alpha b. Next, we update the parameters a. We compute delta a, which uses delta b. Notice that by computing the gradients at the end of the network first, we avoid recomputing the same terms for a that were already computed for delta b. In fact, this is the main idea behind backpropagation. It is simply gradient descent with this efficient strategy to compute gradients. We then compute the gradient for a and update a with this gradient using step size alpha a. This derivation and algorithm easily extend to deeper networks. The delta for the earlier layer is similarly computed recursively using the delta in the next layer. The update on each layer is always of the form of a delta times the input to that layer. Essentially, the network passes back error information stored in the delta at each layer. To make this less abstract, let's look at the backprop algorithm for a particular network. Here's the pseudocode if we use the RailU activation on the hidden layer and a linear unit for the output. First, we compute the error for the output layer. Then, we compute the derivative of the ReLU units with respect to psi. And finally, we use the error signal from the output layer along with U to compute the error signal for the hidden layer. The rest remains the same. And that's it for this video. Today, we derived the gradient of a neural network. We also discussed the main idea of backprop, that computing gradients starting at the output of the network can save computation. This was a pretty detailed derivation. You do not actually need to remember all of these steps. The goal was to give you some insight into the update for a neural network and how that might change with different choices for the loss, activations, and layers. In your assessment, you'll implement the pseudocode given near the end of this video. In the next video, we'll give you a few more tools to make your neural network implementation more effective in practice. Supervised learning systems based on deep neural networks are now the go-to solution for image classification, speech recognition, and natural language processing. Part of the reason is due to the dramatic increases in training data and affordable computation. But to really take advantage of these increases in data and computation, improvements in training were needed. A couple of simple optimization strategies made it much easier to train networks and helped accelerate adoption. We'll talk about these today. By the end of this video, you will be able to understand the importance of initialization for neural networks and describe optimization techniques for training neural networks. Like many machine learning methods, neural networks are trained using an iterative process. This procedure must have some starting point. The choice of this starting point can play a big role in the performance of the neural network. Let's look at an example with only one weight. On the y-axis, we will show the loss function. On the x-axis, we will show values of the weight. As you know, gradient descent will iteratively move the weight towards the nearest stationary point. But neural network loss functions are not quite so simple. If we start in this nearly flat region, it can be hard to make any progress with gradient descent since the gradient is near zero. If instead we start inside this small bowl, then we can quickly find the local optima. But wouldn't it be nice if we could start somewhere here where we can quickly find an even better optimal point? One simple yet effective initialization strategy is to randomly sample the initial weights from a normal distribution with small variance. This way, each neuron has a different output from other neurons within its layer. This provides a more diverse set of potential features. By keeping the variance small, we ensure that the output of each neuron is within the same range as its neighbors. One downside to this strategy is that as we add more inputs to a neuron, the variance of the output grows. We can get around this issue by scaling the variance of the weights by 1 over the square root of the number of inputs. After we have picked the starting point for our network, we start incrementally making small improvements to the weights using stochastic gradient descent steps. Another way to improve training is to consider more sophisticated update mechanisms. Two common strategies are to use the heavy ball method, also called momentum, and vector step size adaptation. Let's talk about momentum first. Imagine this is the trajectory of a two-dimensional weight vector under stochastic gradient descent. Here is the stochastic gradient descent update rule. And here is the update modified to include momentum. Notice it is similar to the regular stochastic gradient descent update plus an extra term called the momentum, m. The momentum term summarizes the history of the gradients using a decaying sum of gradients with decay rate lambda. If recent gradients have all been in similar directions, then we gain momentum in that direction. This means we make a large step in that direction. If recent updates have conflicting directions, then it kills the momentum. The momentum term will have little impact on the update, and we will make a regular gradient descent step. Momentum provably accelerates learning, meaning it gets to a stationary point more quickly. Another potential improvement is to use a separate step size for each weight in the network. So far, we have only talked about a global scalar step size. This is well known to be problematic because this can result in updates that are too big for some weights and too small for other weights. Adapting the step sizes for each weight based on statistics about the learning process in practice results in much better performance. Now, how does the update change? The change is very simple. Instead of updating with a scalar alpha, there's a vector of step sizes, indexed by t to indicate that it can change on each time step. Each dimension of the gradient is scaled by its corresponding step size instead of the global step size. There are a variety of methods to adapt a vector of step sizes. You will get to implement one in your assignment. That's it for this video. Today we discussed ways to improve the training of neural networks. Specifically, we discussed one strategy for initializing the weights in a neural network and how to accelerate learning using momentum and step size adaptation. Now you're all set to implement a TD agent with a neural network. Hope you have fun!
Hi, I'm David Silver, and I'm going to talk about deep reinforcement learning. So let's remind ourselves why we care about reinforcement learning. Reinforcement learning is a very general purpose framework that lets us think about all kinds of different decision-making problems. So it really provides a way to think about any problem where there's an agent, and that agent gets to take actions in the world. And importantly, that agent's actions actually affect the world, and the world in turn changes as a result and gives some observations back to the agent. And the agent gets to choose the actions that maximize its performance in the world that's measured by some kind of reward signal. So this is such a general problem it can be applied to all kinds of things, from robots to games to financial transactions, whatever you think of. Reinforcement learning is this problem framework that lets us do all of those things. So deep learning is a way to, it's actually a general purpose framework to help us solve a wide variety of problems. It's a way to think about representation learning in a very general way. In particular, if we're given an objective, then deep learning gives a way to build up a representation that actually achieves that objective. A way to start with these inputs that kind of filter into the system and build up some kind of features that help to understand those inputs in a way that helps to solve the problem. Using minimal domain knowledge. You don't have to put a lot of knowledge into the system. You just pass something in, like an image of something like a cat or a dog, and the system builds up features to understand patches of this image, and then more complicated features, and eventually comes up with a decision, for example, to say whether this thing is a cat or a dog. So if we put these two things together, deep reinforcement learning is the combination of the two. Really, we're trying to seek an agent that can solve any human level task. That's our ultimate goal here. That's why many of us are interested in artificial intelligence. And if we want to achieve that goal, well, how can we do it? Well, the problem can be defined by reinforcement learning, but deep learning maybe gives us the mechanism that helps us to get there. So RL is like the problem, and deep learning is more like the solution. And so here's a big conjecture, and the big conjecture is that RL plus DL, if we put these two things together, it gives us a recipe that can carry us maybe most of the way towards our big goal, our big ambitions of being able to solve any of these problems. So let's just dive in a little bit to understand what deep learning is all about. So the main piece of deep learning is this thing called a neural network. And a deep neural network really is just something that's you can think of as a multi-layered function, a compositional function, a function of a function of a function. And so if we just unpack that a little bit, it's made up of a few pieces. We start off with some input that goes into the system. That might be your image describing whether this thing is a cat or a dog. And that gets processed by a bunch of different functions to give you these kind of internal states or features. And each of those things takes weights, these W's that kind of tell you what that function should actually do, the parameters of the function. And then that gets processed by a series of different functions until eventually this deep neural network outputs, after all of these different layers of computation, some kind of output describing what the system actually thinks, like, is this a cat or a dog? And as a result of that, there's one final step, which is an important step, which defines the objective of the system, what it's really trying to do. And that we call the loss. It's a number saying, how well this system did, typically a scalar. 1 if you classified this correctly, and 0 if you got it wrong, as an example. Now, the special thing about these deep neural networks is that you can actually not just compute these things in the forward direction, but you can actually reverse the flow of all of that information to work out, which of these parameters led to that loss being good or bad. We can understand, if I was to tweak these parameters in a particular direction, how would those change in parameters actually lead to the output changing and lead to that causing a particular loss? Would it lead to me, predicting this thing being a cat more or a dog more? And the way we do that is just by reversing the direction of flow and using the chain rule of calculus to compute the gradient of this whole system. And that is known as backpropagation. And so the main idea of training a deep neural network is actually just to use this gradient to adjust the parameters. So we compute the gradient of the loss with respect to the parameters. And that you can think of as kind of pointing us in the direction that kind of goes down the hill in terms of, think of this big landscape that's describing, for each point in the landscape is one potential choice of your parameters. And the gradient kind of tells you which direction is going to take you down that landscape, where the height of that landscape is really telling you how good it is. And downhill might be better with your lower error. We want to move down this landscape by following the gradient down to the point that has the lowest error. And so we just move the parameters in that direction, and that really is the fundamental idea behind training a neural network. That's the whole idea of deep learning. Okay, so let's get back to RL again to understand how we can actually put these pieces together to really try and do something amazing. So if we think about RL agents, it's really useful to understand the anatomy of an RL agent. So the way I think about this is that there's these major components that may or may not be inside our agent. And that really defines the kind of category of what type of agent it is. So it might have a policy inside it that determines that agent's behavior, in which case we say this is a policy-based approach to RL. It may have a value function inside it, which kind of describes the agent's predictions about how much reward it will get, or potentially other terms. And in that case, we call it a value-based RL agent. And it might have a model inside it, something saying how the agent thinks the environment works, what it thinks is going to happen next. And so if it has a model inside it, we say it's a model-based approach to RL. We can apply the combination of deep learning and reinforcement learning by essentially using deep neural networks as a function approximator. And that function approximator can be used to represent any one of these three kind of major components of reinforcement learning. It could be used to represent the policy, it could be used to represent the value function, or it could be used to represent the model. Now, to train this system, the main idea is really that we have to pick a loss function. We have to pick an objective that describes what we really want in terms of one of these three kind of families of reinforcement learning algorithms. So if we're doing policy-based reinforcement learning, then, for example, we might choose to follow the policy gradient. If we're doing value-based reinforcement learning, we might choose to minimize the TD error, the temporal difference error. And if we were doing model-based reinforcement learning, we might choose to minimize the next step prediction error. And so what do we do? What's the algorithm? Well, the algorithm's very simple. Just like in deep learning, all we have to do is to optimize that loss function by gradient descent, following this landscape down and down and down and down until our loss gets lower and lower and lower, and we're doing better and better and better. So if we put those things together, it gives us a recipe for achieving all kinds of interesting things in reinforcement learning. And some of those have actually led to some of the exciting success stories that we've seen in recent years. So for example, it's possible to use a deep reinforcement learning approach to try and play games to very high levels. So we've seen agents that are able to defeat the human world champions in the game of Go, and indeed in other games like chess and so forth. Or taking this into the modern era, you might want to play against in video games as well. So we have deep reinforcement learning agents that are able to play 50 or more completely different games from the Atari system. And recently we've had a system which was able to play the very challenging game of StarCraft. This is one of the most challenging video games for humans. But it's not just games that these things can do. They can have impact on all kinds of applications as well. So for example, we've seen deep reinforcement learning agents that can learn to manipulate objects with a great deal of dexterity. We've seen deep reinforcement learning agents which are able to solve chemical synthesis problems by an approach known as retrosynthesis. Or we've seen deep reinforcement learning agents that actually go out and trade in the real world, like actually algorithmically deciding what to do on these trading floors. So in conclusion, when we combine the problem of reinforcement learning with the solution approach of deep learning, and we use these deep learning methods to provide us with a powerful toolkit for function approximation, we actually have a very flexible and powerful approach that can take us a long way towards solving many of the problems that we care about in AI.
This week, we discuss methods for representing large and possibly continuous state spaces, ways to construct features. A representation is an agent's internal encoding of the state. The agent constructs features to summarize the current input. Whenever we are talking about features and representation learning, we are in the land of function approximation. This brings us to the left side of our course map. First, we introduce course coding. Course coding is related to state aggregation. It groups together neighboring states where each grouping can have an arbitrary shape. One particular example of a two-dimensional course coding is represented by these overlapping circles. Each circle is a feature that is 1 when the state is inside the circle and 0 when the state is outside the circle. Next, we discuss a particular type of course coding called tile coding. Tile coding generates features using a set of overlapping grid. Each grid is called a tiling. A tiling itself has no overlap or space between the squares. Only one feature can be active at a time. By stacking multiple offset tilings, we can discriminate between different states. The shape, size, and number of tilings help us balance generalization, discrimination, and computational efficiency. We then discussed a way to learn the representation online with neural networks. With course coding techniques, the representation is fixed before learning. A feed-forward neural network uses a series of layers to produce a representation. In each layer, multiple neurons receive the same input and produce distinct outputs. These outputs are then fed to the next layer, and the process repeats. Each neuron computes its output by taking a weighted sum of the inputs and passing the sum through an activation function. To train a neural network, we use an iterative process called gradient descent. We pass the inputs into the network to produce predictions. Then we compare those predictions to the outputs and compute our loss function. Finally, we compute the derivative of the loss function and apply our learning rule to the weights. Next week, we'll talk about learning to maximize reward with function approximation. See you then. In this video, we get to see episodic SARSA in action on the continuous state domain. We'll visualize the learned values and gain some intuition about the solutions learned by SARSA. By the end of this video, you will gain experience analyzing the performance of an approximate TD control method. Let's look at an example of episodic SARSA on a classic control domain called mountain car. Mountain car is an episodic task where the objective is to drive an underpowered car up the side of a mountain. Gravity is stronger than the car's engine, so the agent cannot directly drive up the mountain. The only way to escape is to first drive backwards up the left slope. Then driving down the hill gives the car enough momentum to drive up the right slope and out. The episode begins with the car in a random location near the bottom of the valley. It ends when the car reaches the flag at the top of the hill. To encourage the agent to finish the episode as quickly as possible, the reward is -1 on each time step, and no discounting is used. The agent can observe the current position and velocity of the car. This is a two-dimensional, continuous valued state. The agent has a choice between 3 actions: accelerate forward, accelerate backward, or coast. For this example, we jointly tilecode the position and velocity to produce features. We use 8 tiles, which means we use 8 by 8 grids for the two-dimensional input space. We use 8 tilings, which means we have 8 overlapping grids. We treat actions independently by using a stacked feature representation. We initialize the weights to 0. This initialization is actually optimistic. This is because the reward is -1 per step, so the values under any policy will be less than 0. In this problem, these optimistic initial values cause extensive and systematic exploration. Because of this, we can act greedily without any additional random exploration. Let's see what the value function looks like after we run the agent for a very long time. Ideally, we would like to plot the value function for every state. However, there's an uncountably infinite number of states, so we'll have to sample the set of states. We'll use the max value in each sampled state. This number tells us the number of steps the agent thinks it will take to escape under its greedy policy. The reward is -1 for each step, so we negate this number to produce the agent's estimate of the number of steps to go from each state. Here's the agent's estimate of the expected number of steps after 9,000 episodes. This is a really long time for this problem, so we're pretty sure the value estimates are about as good as they're going to get. But they're not perfect due to function approximation. The green line represents the goal position, which does not depend on the velocity. Near the goal, if the velocity is large enough, the agent can directly drive out. However, if the agent is near the goal but the velocity is too low, it will take many steps to escape. This is because the agent must first go back down the hill and up the left side again to gain enough momentum to escape. The peak corresponds to the start states, where it takes around 120 steps to reach the flag. This green trajectory reveals the path taken through the state space by the learned policy. The value function looked pretty interesting, but let's look at some learning curves to get better insight into the speed of learning. Let's try SARSA with 3 different values of alpha, so 3 variants of the algorithm. Here we are interested in the steps to goal, which in this case corresponds to the return per episode. We expect the number of steps per episode to decrease with learning. Lower on the x-axis corresponds to better policies, policies that can reach the goal in the fewest steps on average. As always, we average the performance over many independent runs. Here are the results. By 500 episodes, the number of steps per episode has roughly stabilized. All the learning curves exhibit the familiar exponential profile. The smaller step size parameter value of 0.1 results in slower learning, while alpha of 0.5 allowed the agent to learn more quickly and find a better policy over 500 episodes. Notice we divided each alpha value by 8. If we are not using a vector of step sizes, we often scale the step size parameter by the norm of the feature vector. Here we used 8 tilings in our tile coder. That means the number of ones in the feature vector is always 8. As a simple exercise, prove to yourself that 8 corresponds to the L1 norm of the feature vector. Okay, that's enough for today. In this video, we evaluated episodic SARSA with linear function approximation in Mountain Car. See you next time.
The need to balance exploration and exploitation is one of the defining characteristics of the sequential decision-making problem. We've talked about several simple ways to promote exploration in bandits and tabular reinforcement learning. But what about function approximation? Is there anything special about exploration there? Today we'll find out. By the end of this video, you'll be able to describe how optimistic initial values and epsilon greedy can be used with function approximation. Let's do a brief refresher on how we use optimistic initial values in the tabular setting. We initialize our values to be greater than the true values. This is like the agent imagining that it can get more reward by taking that action than it actually can in reality. Typically, initializing the value function this way causes the agent to systematically explore the state action space. As the agent's values become more accurate, they are impacted less and less by this initialization. This is straightforward to implement in a tabular setting, where the update to each state action pair is independent of all the other state action pairs. In function approximation, optimistic initial values corresponds to initializing the weights such that the resulting values are optimistic. In some cases, this is straightforward. For example, when the features are binary, we simply initialize each weight to be the largest possible return. Then, as long as each state has at least one feature active, the value will be optimistic, and likely overly so. In many cases, however, it is difficult to initialize optimistically. For example, in a neural network, the relationship between the final values and the features can be quite complicated. Imagine a network composed of tanh activation functions. The network could output negative values even with positive initial weights. But this isn't the whole story. Depending on how our features generalize, optimistic initial values may not result in the same kind of systematic exploration we see in the tabular case. Consider an extreme example, where we have only one feature that is always 1. We can initialize optimistically, but every update will change the value for all states. This means that before some states are even visited, the value will already have decreased such that it is no longer optimistic. To facilitate systematic exploration, changes to the value function need to be more localized. For example, function approximation with tile coding can produce such localized updates. Neural networks can also provide local updates, but neural networks may also generalize aggressively. In practice, without special consideration, a neural network will lose its optimism relatively quickly. Epsilon greedy is generally applicable and easy to use even in cases with nonlinear function approximation. The only thing epsilon greedy needs are the action value estimates, independent of how they are initialized or approximated. However, epsilon greedy is not a directed exploration method. It relies on randomness to discover better actions near states followed by the current policy. It is therefore not as systematic as exploration methods that rely on optimism. Improving exploration in the function approximation setting remains an open research question. So in this course, we'll stick with this simple strategy. In this video, we talked about how there are many subtleties when combining optimistic initial values and function approximation, and how epsilon greedy can be combined with any function approximation. See you next time! In continuing tasks, we might be interested in extremely long horizon performance. Up until now, we've used discounting and continuing problems to balance short-term performance and long-term gain. However, this is not the only way to formulate the problem. Today, we'll learn about a new way of formulating continuing problems called the average reward formulation. By the end of this video, you'll be able to describe the average reward setting, explain when average reward optimal policies are different from policies obtained under discounting, and understand differential value functions. Today is all about continuing tasks. Imagine a simple task where the states are arranged in two intersecting rings. Let's call this the nearsighted MDP. In most states, there's only one action, so there are no decisions to be made. There's only one state where a decision can be made. In this state, the agent can decide which ring to traverse. This means there are two deterministic policies, traversing the left ring or traversing the right ring. The reward is 0 everywhere except for in one transition in each ring. In the left ring, the reward is +1 immediately after state S. In the right ring, the reward is +2 immediately before state S. Intuitively, you would pick the right action because you know you will get +2 reward. But what would the value function tell us to do? If we use discounting, what are the values of state S under these two different policies? The policy that chooses the left action has a value of 1 over 1 minus gamma to the 5. How do we figure this out? If you write out the infinite discounted return, you will see this is a fairly straightforward geometric series with a closed form solution. See if you can get the same answer that we did. The policy that chooses the right action has a value of 2 times gamma to the 4 over 1 minus gamma to the 5. Let's think of the value of state S under these two-part policies for particular values of gamma. If gamma is 0.5, VL is approximately 1, and VR is approximately 0.1. This means the policy that takes the left action is preferable under this more myopic discount. Let's try a larger value of gamma, 0.9. VL is now approximately 2.4, and VR is approximately 3.2. So now we prefer the other policy. In fact, we can figure out the minimum value of gamma so that the agent prefers the policy that goes right. Gamma needs to be at least 0.841. So the problem here is that the discount magnitude depends on the problem. For this example, 0.85 is sufficiently large. But if the rings had 100 states each, this discount factor would need to be over 0.99. In general, the only way to ensure that the agent's actions maximize reward over time is to keep increasing the discount factor towards 1. Depending on the problem, we might need gamma to be quite large. And remember, we can't set it to 1 in a continuing setting because then the return might be infinite. Now, what's wrong with having larger gamma? Larger values of gamma can also result in larger and more variable sums, which might be difficult to learn. So is there an alternative? Let's discuss a new objective called the average reward. Imagine the agent has interacted with the world for h steps. This is the reward it has received on average across those h steps. In other words, its rate of reward. If the agent's goal is to maximize this average reward, then it cares equally about nearby and distant rewards. We denote the average reward of a policy with R pi. More generally, we can write the average reward using the state visitation mu. This inner term is the expected reward in a state under policy pi. The outer sum takes the expectation over how frequently the policy is in that state. Together, we get the expected reward across states. In other words, the average reward for a policy. In the nearsighted example, the two deterministic possible policies visit either the left loop or the right loop indefinitely. In both cases, the 5 states in each loop are visited equally many times. In the left loop, the immediate expected reward is +0 for all states except 1, which gets +1. This results in an average reward of 1 every 5 steps, or 0.2. Most states in the right loop also have +0 immediate expected reward, but this time the last state gets +2. This gives an average reward of 2 every 5 steps, or 0.4. We can see the average reward puts preference on the policy that receives more reward in total without having to consider larger and larger discounts. The average reward definition is intuitive for saying if one policy is better than another. But how can we decide which actions from a state are better? What we need are action values for this new setting. The first step is to figure out what the return is. In the average reward setting, returns are defined in terms of differences between rewards and the average reward R pi. This is called the differential return. Let's look at what the differential returns are in our nearsighted MDP. The differential return represents how much more reward the agent will receive from the current state in action compared to the average reward of the policy. Let's look at the differential return starting in state S, first choosing action L, and then following pi L afterwards. The average reward for this policy is 0.2. The differential return is the sum of rewards into the future, with the average reward subtracted from each one. This sum starts in state S with the action L. We can compute it by summing to some finite horizon h, then taking the limit as h goes to infinity. We are simplifying things slightly with this limit notation. While the notation provided works in many cases, we need to use a different technique when the environment is periodic. In this case, we compute the return using a more general limit called the Cesaro sum. But this technical detail is not critical. The main point here is the intuition. We find that the differential return is 0.4. Now let's look at the other action. This time, we can break the differential return into 2 parts. First, the sum for a single trajectory through the right loop. We can write the sum explicitly, and it's equal to 1. Then, the sum corresponding to taking the left action indefinitely. This sum is the same as the differential return we just computed, 0.4. Adding the 2 parts together, we find that the differential return is 1.4. So if the agent's policy is to always take the left action, it can observe its differential returns and realize it should switch to taking the right action. Now let's look at the differential returns if the agent's policy is to always take the right action. This policy results in an average reward of 0.4, and the differential return for the policy that takes the right action in state S is minus 0.8. Now what's the differential return for taking the left action once in state S and then taking the right action indefinitely? Like before, we break up the sum into 2 parts. Taking the left loop once results in a sum of minus 1 over the first 5 time steps. Adding the differential return from following pi r from state S, which we found to be minus 0.8, results in our answer of minus 1.8. Once again, we see that the right action is preferred. You may have noticed that the differential returns for pi r were lower than the differential returns for pi l, even though pi r has a higher average reward. This is because the differential return represents how much better it is to take an action in a state than on average under a certain policy. The differential return can only be used to compare actions if the same policy is followed on subsequent time steps. To compare policies, their average reward should be used instead. Interestingly, the differential return is only a convergent sum if the subtracted constant is equal to the true average reward. If a lower or higher number is subtracted, the sum will diverge to positive or negative infinity. Now that we have a valid definition of the return for average reward, we define value functions in the usual way, as the expected return. Similarly, we can also define differential value functions as the expected differential return under a policy from a given state or state action pair. This quantity captures how much more reward the agent will get by starting in a particular state than it would get on average over all states if it followed a fixed policy. Like in the discounted setting, differential value functions can be written as Bellman equations. Conveniently, they look like the previous ones we've seen. They only differ in that they subtract R pi from the immediate reward, and there is no discounting. Many algorithms from the discounted case can be rewritten to apply to the average reward case. For example, differential SARSA is very similar to the SARSA algorithm you've seen before. Let's step through the differences. A key difference is that differential SARSA has to track an estimate of the average reward under its policy and subtract it from the sampled reward in its update. This implementation does so with the incremental averaging techniques we've seen throughout the course. Given this estimate, it then subtracts R bar from the sampled reward in its update. In practice, we can get better performance with a slight modification to this algorithm. Instead of the exponential average of the reward to compute R bar, we use this update which has lower variance. In this video, we introduce the average reward objective and define differential returns and differential value functions for this setting. Next week, we'll talk about another way to optimize this average reward objective. See you then.
I'm Satinder Singh, and thanks Martha and Adam for inviting me for this. So I'm at DeepMind right now. I'm on leave from the University of Michigan. And I'm going to talk about the problem of where do rewards come from in reinforcement learning. Now, when we all study reinforcement learning, we assume the rewards are given and the rest of we study how to optimize those rewards. But it could be an interesting question to ask, where do these rewards come from to begin with? So the way I'm going to set this question up is by talking about the preferences parameters confound. And that's a mouthful, so I'm going to break it down for you. So the starting point when we're doing sort of AI is for an agent designer that has an objective or extrinsic reward function that specifies preferences over agent behavior. So I'm the agent designer, I'm designing an agent, I have preferences over the agent's behavior. That's my objective or extrinsic reward function. And often it's too sparse and delayed. And so the question then becomes, what reward function should I give the agent? What should the agent's reward function be? Where do the rewards come from, in other words? And so when we think about it this way, the single reward function that you read about in reinforcement learning confounds two roles from the designer's point of view simultaneously in reinforcement learning agent. It embodies or it captures preferences, that is, it expresses the agent designer's preferences over behavior. It's also parameters, because through the reward hypothesis, it expresses the RL agent's goals or purposes and therefore becomes parameters of the actual agent behavior. So the same single reward function in the standard RL framework captures two things: preferences by the agent designer over agent behavior, and as parameters of whatever RL algorithm the agent is using to convert the reward function into behavior. And the question that I'm asking is, these roles seem distinct, and should they be confounded into a single reward function? And so the answer I'm going to suggest is that they should not be, though we can imagine two different reward functions. So here's a diagram of the standard reinforcement learning agent where the reward function is assumed to be part of the environment. The critic is part of the environment, and then the agent's task is to optimize some cumulative measure over that reward function. Here's another diagram in which we blow up the agent into, let's call it the organism, in which inside the agent is a critic, which then rewards the agent that then the agent optimizes. And there's an external environment, which played the role of the previous environment in which the extrinsic reward would lie. And of course, when you think of the organism, you think of natural organisms, for example, you would think that evolution would have been able to reach inside us and configure our internal reward function. Hence, it's a locus of adaptation. Okay, so agent reward is internal or intrinsic to the agent because they are parameters, in essence, to be designed by the agent designer in artificial agents or by evolution in natural agents. Okay, so many people think about designing reward function. There are many approaches to it. For example, inverse reinforcement learning is a way of converting expert behavior into a reward function. Reward shaping are ideas about how to change the reward function to make the reward function more efficient for the agent to learn from. Preference elicitation is a way of eliciting preferences or rewards from an agent designer. Mechanism design in economics thinks about how to design rewards, and so on. And there are many other heuristic approaches, often very successful empirically in designing reward functions. I'm going to tell you about a little line of work that I've been pursuing called the optimal reward framework, or the optimal reward problem. So what is the optimal reward problem? Again, as I've been arguing, there are two different notions of reward. One which we can't change because the true reward is the objective reward, denoted here by R sub 0 or R sub O, and then the agent's reward, which is the internal reward, or R sub I. And so the optimal reward problem in English, shown in math in the slides, is the following. Given a space of reward functions, what is the reward function I should give the agent so that in translating the reward function into behavior, the agent ends up optimizing the agent designer's or objective reward function. So that's the optimal reward. If you give me a space of reward functions, you can essentially use any algorithm you want, potentially to search over this space and design or recover or discover the reward function that optimizes the agent's behavior from the agent designer's point of view, or the extrinsic or the objective reward point of view equivalently. So that's the optimal reward problem. And it's a search problem. It's a problem that we can solve in any way. We can think of it as a meta problem, right? An outer loop where you're optimizing the reward, where the inner loop is optimizing the behavior given the reward. And that's what I'm going to show you a couple of quick ideas what we've developed in my lab for optimizing the internal reward. Okay, so here's the sort of first idea. It's a very simple intuition we call PGRD, or policy gradient for reward design. And it stems from the following simple observation. We've always had policy gradient approaches for optimizing an extrinsic reward. Those policy gradient approaches take parameters that specify the policy in some way. One way to think about the intrinsic reward is that it's just parameters that are in effect parameterizing the policy of the agent. And so just as policy gradient methods can optimize parameters of the policy, they can optimize the internal reward function. And that's one approach, is basically using gradients of the extrinsic reward with respect to policy parameters, which are intrinsic reward parameters. And so we did this in a particular paper in NIPS 2010, and I'm going to tell you a little bit about it by this slide. So this slide describes how you can compute the gradient with respect to the intrinsic reward parameters when you do policy gradients. So the first box on top shows you how you can define the gradient of the objective reward along a trajectory with respect to the policy, with respect to the probabilities of taking actions embodied in the policy. And the second part tells you how you can take the gradient with respect to these policy choices or probabilities of actions with respect to the parameters of the intrinsic reward. And it's basically a pretty straightforward iterative process, and you can compute it, and that way the agent can update its intrinsic reward over time as it learns through experience in the environment. So one of the first projects we did was to use, this is in Ichikai 2016, where we showed how you can use this procedure, PGRD, policy gradient for reward design, to optimize the intrinsic reward function to use with UCT as a policy gradient algorithm, as a planning algorithm, to compute behavior given an intrinsic reward. So we have UCT, which is essentially a look-ahead search procedure for computing policies from a model, and UCT has a fixed number of trajectories and a fixed depth that it searches over as parameters, and but it uses an intrinsic reward, and we were able to do gradients through the UCT planning procedure to update the reward function. So I didn't walk through the algorithm details, but we did PGRD with UCT, and here is a slide showing results of 25 Atari games, where the vertical line is if a bar is on the vertical line, that means we were able to just match the performance of UCT, and as bars go to the right, that means we are improving on performance in UCT. And you can see that in most of these games, we were able to improve performance significantly. So the only thing that's being learned in these results is the intrinsic reward function. Recall we're using UCT to plan. So the conversion of intrinsic rewards to behavior is through UCT, which is a fixed planning procedure. The only thing we're learning from experience is the intrinsic reward function, and we can see that we can improve performance significantly. Okay, so this was for doing this over planning with respect to a planning algorithm. Can we do this with respect to a learning algorithm? So that's the next bit of result I'm going to tell you about. This is work presented in Europe in 2018. My students Zheyu Zhang and Zhenyu Guo. And this was exactly the same idea, except now we're going to do it through a learning algorithm rather than through a planning algorithm. It wasn't clear to me to begin with that you can actually take the gradients through a learning procedure to update the intrinsic rewards, because conceptually you can imagine that as you perturb the intrinsic reward, you perturb the dynamics of learning. So what we need to do is take the gradient to that change in dynamics of learning and update the intrinsic reward to update then the learning process. And that's what we showed that we can do through a meta-gradient procedure. So here's a diagram for the agent. In this diagram, the agent has two boxes. The policy box, which will do the actor critic box, which will take an intrinsic reward, or in this case, a sum of an extrinsic reward, and do policy gradients, actor critic, to update the policy. And we're going to use this meta-gradient procedure for updating the intrinsic reward. Okay, so I'm going to skip the notation, but there is a specific way of updating the parameters of the intrinsic reward, given that we're doing updating the parameters of the policy using actor critic. And so the first equation shows you a standard actor critic update. Essentially, I think this is showing the reinforced version of the actor critic update. And the second set of equations shows you how we update the parameters of the intrinsic reward with respect to the update of the policy parameters. And so we can move the intrinsic reward parameters in a direction that improves the performance of the learned policy. Okay, and here's just some results where we did this on a bunch of Atari games. You can see the names on the x-axis. On the y-axis, we show the percentage improvement we get over using just the extrinsic reward with the same actor critic architecture that we use with the learned intrinsic rewards. And so we can see that learning the intrinsic rewards improves performance quite significantly. Okay, so I'm going to stop and just conclude by saying that as we think about the reinforcement learning problem, the textbook and all the lectures you hear about start by assuming the reward function is given, and the goal of the agent is to convert that reward function into good behavior. And the question we asked in this little snippet is, how do we design those reward functions effectively? And the bottom line answer that this little snippet tells you about is a gradient procedure for updating the intrinsic reward so that we can learn better intrinsic reward. This could be useful in many different ways. The way I emphasize today is that the agent can be bounded in many different ways, and so the intrinsic reward is a method for overcoming those bounds. A value alignment between user and the agent designer. This could be thought of in that way. It can also be thought of as a way of addressing problems in continuing or lifelong learning.
This week, we talked about how to do control when using function approximation. Let's go over the main ideas. First, we showed you how to estimate action values with function approximation. If the action space is discrete, it's probably easiest to stack the state features. If the action space is continuous, or you want to generalize over actions, the action can be passed as an input like any other state variable. Let's get some context about the next part of the module by looking at the algorithm map. function approximation puts us on the left side of the map. The focus of the first lecture was on the control algorithms in the bottom left corner: SARSA, expected SARSA, and Q-learning. These are all extensions of the tabular control algorithms we covered in Course 2. The only difference between these algorithms and their tabular counterparts are the update equations. The updates are all adapted for function approximation in the same way, using the gradient to update the weights. We also saw how episodic SARSA could be used to solve the mountain car problem. In this case, the larger step size of 0.5 was able to learn more quickly. Next, we talked about exploration. Optimistic initialization can be used with some structured feature representations, like tile coding. But in general, it's not clear how to optimistically initialize values with nonlinear function approximators, like neural networks. And it might not behave as expected. For example, the optimism may fade too quickly. Epsilon greedy can be used regardless of the function approximator. Finally, we talked about a new way to think about the continuing control problem. Instead of maximizing the discounted return from the current state, we can think about maximizing the average reward that a policy receives over time. We define differential returns and differential values. These enable the agent to assess the relative value of actions in the average reward setting. Finally, we introduce differential semigradient SARSA that approximates differential values to learn policies. Differential SARSA is also in the left half of the algorithm map, but unlike the algorithms we covered earlier in the week, it uses the average reward framework. That's all for this week. We extended our tabular control algorithms to function approximation, discussed how exploration changes, and introduced a new way to think about the control problem. Next week, we'll talk all about how to do reinforcement learning without learning a value function. See you then.
So far, all the methods we've looked at for learning good policies estimate action values. Every control algorithm we've studied was built on the framework of generalized policy iteration. In this module, we'll explore a new class of methods where the policies are parameterized directly. By the end of this video, you'll be able to understand how to define policies as parameterized functions and define one class of parameterized policies based on the softmax function. Let's think about what it means to specify a policy directly. We'll do this in mountain car. Previously, we used epsilon greedy to convert approximate action values into a policy. But we could also consider a policy which maps states directly to actions without first computing action values. For example, in mountain car, we can define such a policy. Simply choose accelerate right when the velocity is positive, and otherwise choose the accelerate left action. Put another way, this policy accelerates in whatever direction we are already moving. In fact, this simple energy pumping policy is close to optimal. This policy does not make use of action values at all. But this was just an example to stimulate your intuitions and to show you that we don't need action values to construct policies. We are not actually going to specify policies by hand. Rather, we will learn them. We can use the language of function approximation to both represent and learn policies directly. We'll use the Greek letter theta for the policy's parameter vector. This distinguishes it from the parameters w for the approximate value function. We'll use the notation pi of a given s and theta to denote the parameterized policy. For a given input state and action, the parameterized policy function will output the probability of taking that action in that state. This mapping will be controlled by the parameters theta. The parameterized function has to generate a valid policy. This means it has to generate a valid probability distribution over actions for every state. Specifically, the probability of selecting an action must be greater than or equal to 0. And for each state, the sum of the probabilities over all actions must be 1. It requires some thought to satisfy these conditions for a parameterized function. For example, this means we cannot use a linear function directly, like we did with value function approximation. There is no easy way to guarantee that a linear function will sum to 1. Instead, we will need to restrict the class of functions we can use to construct policies. Let's consider a simple but effective way to satisfy these conditions called a softmax policy. Here's the definition of a softmax policy. The function h shown here is called the action preference. A higher preference for a particular action in a state means that the action is more likely to be selected. The action preference is a function of the state and action, as well as a parameter vector theta. Computing the probability of selecting an action with the softmax is simple. We take the action preference, exponentiate it, and then divide by the sum over all the actions for the same thing. The exponential function guarantees the probability is positive for each action. The denominator normalizes the output of each action such that the sum over actions is 1. The action preference can be parameterized in any way we like, since the softmax will enforce the constraints of a probability distribution. For example, the action preferences could be a linear function of the state action features, or something more complex like the output of a neural network. Here's what we get when we pass a particular set of action preferences through the softmax. The input preferences can be arbitrarily large, or even negative. If one preference is much larger than all the others, the action probability will be close to 1. No matter how big the preference gets, the probability will never be greater than 1. If one preference is very small, the softmax policy will still select the action with non-zero probability. For example, if the preference is negative and the other is positive, the negative action will still have non-zero probability. Finally, actions with similar preferences will be chosen with near equal probability under a softmax policy. It's important to distinguish between action preferences and action values. Preferences indicate how much the agent prefers each action, but they are not summaries of future reward. Only the relative differences between preferences are important. For example, we could add plus 100 to all the preferences and it would not matter. An epsilon greedy policy derived from action values can behave very differently than a softmax policy over action preferences. In epsilon greedy, the action corresponding to the highest valued action is selected with high probability. The probability of selecting all the other actions is quite small. Actions with nearly the same but lower action value are selected with much lower probability. On the other hand, actions with very poor action values are still selected frequently due to the epsilon exploration step. So even if the agent learns an action has terrible consequences, it will continue to select that action much more frequently than it would under the softmax policy. That's it for this video. You should now understand we can parameterize policies directly, that we need to define parameterizations that produce valid probability distributions, and understand the softmax policy parameterization. See you next time. You now know it's possible to learn parameterized policies directly. This means we can have more flexibility in how we solve our problems. Now we consider learning approximate values and learning approximate policies. But is it really helpful to directly learn policies? After watching this video, you'll be able to understand some of the advantages of using parameterized policies. There are many advantages to directly learning the parameters of a policy. First, the agent can make its policy more greedy over time autonomously. Why would you want that? Well, in the beginning, the agent's estimates are not that accurate. So you would want the agent to explore a lot. As the estimates become more accurate, the agent should become more and more greedy. Recall the epsilon greedy policy we used before. The epsilon step chooses a random action to ensure continual exploration. However, the epsilon probability puts a cap on how good the resulting policy can be. We could, of course, switch to a greedy policy when we think the agent has explored adequately. But we want our agents to be autonomous. We don't want them to rely on us to decide when exploration is done. We can avoid this issue with parameterized policies. The policy can start off stochastic to guarantee exploration. Then, as learning progresses, the policy can naturally converge towards a deterministic, greedy policy. A softmax policy can adequately approximate a deterministic policy by making one action preference very large. In the tabular setting, we learn there is always a deterministic optimal policy. In function approximation, we may not be able to represent this deterministic policy. Instead, the optimal approximate policy might be a stochastic policy. This suggests it might be useful to learn stochastic policies. We can see why this is true by considering an example. Imagine the agent is in a corridor, it always starts in the far left state. In the left and right states, the actions left and right have their usual consequences. In the middle state, however, the left and right actions are switched. Moving left will take the agent right. Moving right takes the agent to the left state. The reward is -1 in every step, and the task is episodic. Imagine the function approximation treats all these states as the same. All three states share the same approximate value. If we choose to limit ourselves to deterministic policies, we would have no choice but to pick the same action in all the states. This would give us just two choices: always move left or always move right. If we always move left, we will never leave the start state, so the expected return for that policy is -infinity. If we always move right, we will reach the middle state and then move back to the start state and continue this forever. So the expected return is also -infinity. If we are allowed to choose actions stochastically, however, we can do much better. We may get stuck for a while, but as long as each action has a non-zero probability, we will eventually reach the terminal state. In fact, the best policy under this function approximation is a little particular. Choose the right action 59% of the time and the left action the rest of the time. This policy achieves an expected return of around -11.6, clearly better than -infinity. This example may seem a bit contrived, but similar situations can arise in the real world. For example, in our own lab, a robot got stuck in the corner of the room because it had a deterministic policy and a limited function approximator. Sometimes the policy is more simple than the value function. Remember the mountain car problem. We spent a lot of time designing a value-based agent to learn an optimal policy. However, in this problem, the energy pumping policy we saw previously is nearly optimal. The agent simply selects its action in agreement with the current velocity. If the velocity is negative, then the agent takes the accelerate left action. If the velocity is positive, then the agent takes the accelerate right action. This policy allows the agent to quickly escape from the valley. As you can see, this is quite a simple policy. The value function, on the other hand, is quite complex. That's it for today. You should now understand that parameterized stochastic policies are useful because they can autonomously decrease expiration over time. They can avoid failures due to deterministic policies with limited function approximation. And sometimes the policy is less complicated than the value function. In upcoming videos, we'll see that there is not a strict distinction between action value methods and policy-based methods. In fact, we can use action values to make it easier to learn a parameterized policy. See you then.
Now that we've introduced the idea of parameterizing policies directly, we're ready to talk about how we can learn to improve a parameterized policy. Just like with action value-based methods, the basic idea will be to specify an objective and then figure out how to estimate the gradient of that objective from an agent's experience. After watching this video, you'll be able to describe the objective for policy gradient algorithms. Formulating an objective for learning a parameterized policy is in some sense more straightforward than it was for action value-based methods. We've said many times that the ultimate goal of reinforcement learning is to learn a policy that obtains as much reward as possible in the long run. It turns out that when we parameterize our policy directly, we can also use this goal directly as the learning objective. Throughout this specialization, we've introduced a few different interpretations of what it means to obtain as much reward as possible in the long run. For the episodic case, we can use the undiscounted return, which is the sum of rewards over a whole episode. For the continuing case, we introduce the discounted return, which places more emphasis on immediate reward in order to keep the sum finite. Most recently, we introduced the average reward formulation. Here, we maximize the long-term average of the reward. The appropriate return here is the sum of the differences between the immediate reward and its average. Because the long-term average is subtracted, this sum is finite, even without discounting. Here we have three potential problem formulations to consider. We are going to restrict our attention to the continuing setting with average reward. Remember what our aim is here, to find a way to directly optimize the parameters of a policy. The first step is to write the average reward objective in a form that we can optimize. Previously, we estimated the average reward to learn action values in an average reward variant of SARSA. Now, our aim is to learn a policy that directly optimizes average reward. Toward this aim, let's start by writing the average reward under a policy in a more useful form. We can write the average reward achieved by a particular policy pi like this. Let's break this formula down, starting from the inner sum and moving out. This inner sum gives the expected reward if we start in state S and take action A. This is simply the sum over all rewards we might receive, weighted by their probability from S and A. We sum over next state's S prime to get marginal probabilities over the reward. The next level of the summation is over all possible actions, weighted by their probability under pi. This gives us the expected reward under the policy pi from a particular state S. Finally, we get the overall average reward by considering the fraction of time we spend in state S under policy pi. The distribution mu provides these probabilities. The expected reward across states is the sum over S of the expected reward in a state weighted by mu of S. R pi is our average reward learning objective. Our goal with policy optimization will be to find a policy which maximizes the average reward. Our basic approach will be to estimate the gradient of the objective with respect to the policy parameters and adjust the parameters based on this estimate. The class of methods that use this idea are often referred to as policy gradient methods. Up until now, we've used a very different approach. We use the generalized policy iteration framework to learn approximate action values. Then, we use these approximate values indirectly to infer a good policy. Now, we're interested in learning policies directly. There's also a superficial difference, in that before we were minimizing the mean squared value error, and now we are maximizing an objective. That means we will want to move in the direction of the gradient rather than the negative gradient. There are a few challenges in computing this gradient, however. The main difficulty is that modifying our policy changes the distribution mu. This contrasts value function approximation, where we minimize mean squared value error under a particular policy. There, the distribution mu was fixed. It does not change as the weights in the parameterized value function change. We were therefore able to estimate gradients for states drawn from mu by simply following the policy. This is less straightforward when mu itself depends on the policy we are optimizing. Luckily, there's an excellent theoretical answer to this challenge called the policy gradient theorem. We'll talk more about that soon. That's it for this video. You should now understand that we can use the average reward as an objective for policy optimization. In upcoming lectures, we will discuss how to actually optimize this objective from sampled experience. See you then! We just discussed an objective for policy optimization. The next step is to figure out how the agent can optimize it based on its own experience. In this video, we will describe the policy gradient theorem. This is a key theoretical result. It allows us to write the gradient of the average reward so that it is easier to estimate from experience. After watching this video, you will be able to describe the result of the policy gradient theorem and understand the importance of the policy gradient theorem. To optimize the mean squared value error, we used methods based on stochastic gradient descent. We estimate the negative of the gradient of our objective and adjust the weights of the value function in that direction. Policy gradient methods use a similar approach, but with the average reward objective and the policy parameters theta. We want to maximize the average reward rather than minimizing it. This means we do gradient ascent and move in the direction of the positive gradient. Remember that a simple recipe for solving a problem is to first specify an objective, then estimate the gradient of that objective, and finally adjust the weights in that direction. Step 1 is done. Now the next step is to estimate the gradient of our objective. Recall the average reward objective. Let's compute the gradient. We can apply the product rule of calculus to the objective to yield two terms. This looks pretty complex, so let's look at it a bit more closely. The first term involves the gradient of the stationary distribution over states. Unfortunately, the gradient of mu is not straightforward to estimate. The stationary distribution mu depends on a long-term interaction between the policy and the environment. Luckily, the policy gradient theorem gives us a simpler expression for this gradient. Here we show the result of the theorem. It's worth walking through this expression. In the inner sum, we have the gradient of the policy times the action value function. Let's try to understand this term a little better. The gradient of the policy is easy to compute as long as our policy parameterization is differentiable. The gradient of the policy tells you how to adjust your parameters to increase the probability of a certain action. Consider the simple grid world shown here. As usual, the agent can move up, down, left, or right. For simplicity, let's assume the policy is controlled by just two parameters. The parameters are currently set to the point marked here. The arrows indicate the agent's action probabilities in a particular state with the current parameter settings. The gradient for the up action might look something like this on the plot. The gradient tells us how to change the policy parameters to make that action more likely to be selected in the given state. By moving the parameters in the direction of the gradient, we increase the probability for the up action. This necessarily means decreasing the probability of some of the other actions. Different actions have different gradients. For example, the gradient of the left action probability may look like this. Moving the parameters in that direction will increase the probability of the left action and decrease the probability of some of the other actions. This might all sound a bit abstract, but we will show concrete examples of computing this gradient in the coming lectures. Now let's bring some reward into the situation and think about what this whole term means. This is a sum over the gradients of each action probability, weighted by the value of the associated action. Imagine we've added a rewarding state in the bottom right. The up and left actions move away from it and should have negative value. The down and right actions move toward it and should have positive value. The precise values will depend on the current policy, but let's say they look something like this. The weighted sum gives a direction to move the parameters that decreases the probability of moving up or right, since their value is negative, while increasing the probability of moving down or left, since their value is positive. That direction might look like this. The gradient expression given by the policy gradient theorem takes this expression and sums it over each state. This gives the direction to move the policy parameters to most rapidly increase the overall average reward. And that's it. We now have a simple expression for the gradient. Importantly, this expression does not contain the gradient of the state distribution mu, which is challenging to estimate. The proof of the policy gradient theorem can be found in the course textbook. As we will see in the next lecture, this gradient is straightforward to estimate. That means we will be able to build an incremental policy gradient algorithm using an agent's experience. That's it for this video. You should now understand how the policy gradient theorem gives us an expression for the gradient of the average reward and understand the terms in the gradient. See you next time. We have an objective for policy optimization. We also have the policy gradient theorem, which gives us a simple expression for the gradient of that objective. In this video, we'll complete the puzzle by showing how to estimate this gradient using the experience of an agent interacting with the environment. After watching this video, you will be able to derive a sample-based estimate for the gradient of the average reward objective. We want to derive a gradient ascent algorithm for our policy. We have our objective and its gradient due to the policy gradient theorem. Now we need to figure out how to approximate this gradient. In fact, what we will do is get a stochastic sample of the gradient. Recall this expression for the gradient of the average reward. Computing the sum over states is really impractical, but we can do the same thing we did when deriving our stochastic gradient descent rule for policy evaluation. We simply make updates from states we observe while following policy pi. This gradient from state st provides an approximation to the gradient of the average reward. As we discussed before for stochastic gradient descent, we can adjust the weights with this approximation and still guarantee we will reach a stationary point. This is what the stochastic gradient descent update looks like for the policy parameters. We could stop here, but let's simplify this further. Let's re-examine this from a perspective based on expectations. This will help us simplify the update and give you more insight into why the update makes sense. Notice that the sum over states weighted by mu can be rewritten as an expectation under mu. Recall that mu is the stationary distribution for pi, which reflects state visitation under pi. In fact, the states we observe while following pi are distributed according to mu. By computing the gradient from a state st, we get an unbiased estimate of this expectation. Thinking about our stochastic gradient as an unbiased estimate suggests one other simplification. Notice that inside the expectation, we have a sum over all actions. We want to make this term even simpler and get rid of the sum over all actions. If this was an expectation over actions, we could get a stochastic sample of this too, and so avoid summing over all actions. Here we're going to see how we can get an unbiased gradient estimate using only one action, AT, which is the action taken by the agent. It would be nice if the sum over actions was weighted by pi, and so was an expectation under pi. That way, we could sample it using the agent's action selection, which is distributed according to pi. It turns out this is an easy problem to solve. To get a weighted sum corresponding to an expectation, we can just multiply and divide by pi of a given s. Now we have an expectation over actions drawn from pi for this term. The new stochastic gradient ascent update now looks like this. As an aside, it is common to rewrite this gradient as the gradient of the natural logarithm of pi. This is based on a formula from calculus for the gradient of a logarithm. Using this rule, we get that the gradient of ln pi equals the gradient of pi over pi. So this update is equivalent to what we started with. But why do we do this? One reason is that it is actually simpler to compute the gradient of the logarithm of certain distributions. The other, less important reason is simply that it lets us write this gradient more compactly. In the end, it is just a mathematical trick, so don't let it distract you from the underlying algorithm. We now have something that looks like many of the learning rules used in this course. We adjust the parameters theta proportionally to a stochastic gradient of the objective. We use a step size parameter alpha to control the magnitude of the step in that direction. So alpha has the same role it always has. And that's it. We now have a nice clean update rule to learn the policy parameters. The last thing to talk about is how to actually compute the stochastic gradient for a given state and action. We just need two components, the gradient of the policy and an estimate of the differential values. The first is easy. We know the policy and its parameterization, and so can compute its gradient. The action value can be approximated in a variety of ways. For example, we could use a TD algorithm that learns differential action values. In an upcoming video, we will go through one particular choice in detail, as well as how to compute the gradient for specific policy parameterization. In this video, we derived a policy gradient learning rule for the average reward setting. In the next video, we will see how to use this rule.
Do we have to choose between directly learning the policy parameters and learning a value function? No. Even within policy gradient methods, value learning methods like TD still have an important role to play. In this setup, the parameterized policy plays the role of an actor, while the value function plays the role of a critic, evaluating the actions selected by the actor. These so-called actor-critic methods were some of the earliest TD-based methods introduced in reinforcement learning. After watching this video, you will be able to describe the actor-critic algorithm for control with function approximation for continuing tasks. We finished off the last video with this expression for the policy gradient learning rule. But we don't have access to QPy, so we'll have to approximate it. We can do the usual TD thing, the one-step bootstrap return. That is, the differential reward plus the value of the next state. As usual, the parameterized function v hat is a learned estimate of the value function. In this case, v hat is the differential value function. This is the critic part of the actor-critic algorithm. The critic provides immediate feedback. To train the critic, we can use any state value learning algorithm. We will use the average reward version of semi-gradient TD. The parameterized policy is the actor. It uses the policy gradient update shown here. We could use this form of the update, but there is one last thing we can do to improve the algorithm. We can subtract off what is called a baseline. Instead of using the one-step value estimate alone, we can subtract the value estimate for the state st to get the update that looks like this. V hat of st is the baseline in this case. Notice that this expression is equal to the TD error. The expected value of this update is the same as the previous one. Why is this? Let's take the expectation of the update conditioned on a particular state S at time t. Taking the expectation of the sum is the same as the sum of the expectations. We can use this to separate out the expectation of our original term from the expectation which involves the subtracted value function. It turns out the expectation of the second term is 0. So we can add this baseline to the update without changing the expectation of the update. You can verify this for yourself. To start, write the expectation as the sum of fractions and pull the v hat term out of the sum. We'll leave this as an exercise. So why do we add this baseline if the update is the same in expectation? Subtracting this baseline tends to reduce the variance of the update, which results in faster learning. This update makes sense intuitively. After we execute an action, we use the TD error to decide how good the action was compared to the average for that state. If the TD error is positive, then it means the selected action resulted in a higher value than expected. Taking that action more often should improve our policy. That is exactly what this update does. It changes the policy parameters to increase the probability of actions that were better than expected according to the critic. Correspondingly, if the critic is disappointed and the TD error is negative, then the probability of the action is decreased. The actor and the critic learn at the same time, constantly interacting. The actor is continually changing the policy to exceed the critic's expectation, and the critic is constantly updating its value function to evaluate the actor's changing policy. With the policy update in place, we are ready to go through the full algorithm for average reward actor-critic. To start, we specify the policy parameterization and the value function parameterization. For example, we might use tile coding to construct the approximate value function and a softmax policy parameterization. We will need to maintain an estimate of the average reward, just like we did in the differential SARSA algorithm. We initialize this to 0. We can initialize the weights and the policy parameters however we like. We initialize the step size parameters for the value estimate, the policy, and the average reward. And they could all be different. We get the initial state from the environment and then begin acting and learning. On each time step, we choose the action according to our policy and receive the next state and reward from the environment. Using this information, we compute the differential TD error and update our running estimate of the average reward. We update the value function weights using the TD update. Finally, we update the policy parameters using our policy gradient update. And that's it. This algorithm is designed for continuing tests, so we can run it indefinitely and continue to improve the policy forever. That's it for this video. You should now understand that it is useful to learn a value function to estimate the gradient for the policy parameters, and that the actor-critic algorithm implements this idea with a critic that learns a value function for the actor. Bye for now. Actor-critic elegantly mixes direct policy optimization, value functions, and temporal difference learning. The actor-critic method we discussed previously was quite general. We didn't specify the function approximation, nor the policy parameterization. Today, we discuss one specific implementation, actor-critic with linear function approximation and a softmax policy parameterization. By the end of this video, you'll be able to derive the actor-critic update for a softmax policy with linear action preferences, and implement this algorithm. Previously, we introduced the actor-critic algorithm. That algorithm combines policy evaluation, which is the critic, and the policy gradient rule to update the policy, which is the actor. The critic uses semi-gradient TD. The actor uses the TD error from the critic to update the policy parameters. All of this is a little bit high-level and abstract. Let's consider a specific implementation. Let's build an algorithm for a finite set of actions and continuous states. A common choice of policy parameterization for finite actions is the softmax policy we discussed before. We can use function approximation to represent the preferences. The parameters of this function are the policy parameters denoted by theta. So our policy gradient learning rule will update theta. We use a softmax policy that exponentiates the preferences and divides by the sum. This guarantees the resulting action probabilities are positive and sum to 1. Notice the policy is written as a function of the current state. This is like having a different softmax distribution for each state. Watch the agent move through the state space. The state-dependent action preferences give rise to potentially different distributions for each state. To select an action, we follow a simple procedure. In the current state, we query the softmax for each action. This generates a vector of probabilities, one entry for each action. Given this vector, we pick an action proportionally to these probabilities. Now let's discuss how our parameterization choices impact the value function, the action preferences, and our update equations. Let's use the same features for our value estimates and the policy. Remember, the critic updates an estimate of the state value function. So the critic only requires a feature vector characterizing the current state. The actor's action preferences depend on the state and action. So our action preference function requires a state action feature vector. We have encountered this issue before. We use the same strategies before, stacked state features. That is, we use a copy of the state feature vector for each action. The size of the policy parameter vector theta is larger than the weights w used by the critic. Since there are 3 actions, this is 3 times larger. Now let's look at the update equations for the actor and the critic with our linear softmax parameterization. The first one is easy. The gradient of the linear value function is just the feature vector. So the critic's weight update is just alpha times the TD error times the feature vector. Same old semi-gradient TD. The actor's update to the preferences requires a bit more thought. Luckily, the gradient is not so bad. We will leave out the derivation and just give you the final result. You can verify it if you like. The gradient has 2 parts. The first is the state action features for the selected action. The second part is the state action features multiplied by the policy summed over all actions. That's it for this video. Today we discussed a specific implementation of actor-critic. Now you know everything you need to know to implement this algorithm on your own. Next time we'll try this algorithm out and see how it works. I can't wait. In this video, we will see how the actor-critic algorithm works on a classic control task, the pendulum swing-up problem. By the end of this video, you will be able to design a function approximator for an average reward actor-critic algorithm and analyze the performance of an average reward agent. Today we'll investigate the pendulum swing-up task. The agent controls the pendulum. The controls are simple. The agent can apply torque on a pivot point marked by the black dot. The goal is to get the pendulum to balance upright. The pendulum starts in its rest position, hanging down with no velocity. The pendulum can move freely, subject only to gravity and the actions applied by the agent. The state of the pendulum is the angle of the pole and the angular velocity. Both are real valued quantities. Our simulation has just 3 discrete actions. Apply a constant angular acceleration clockwise, counterclockwise, or apply no angular acceleration. We use a softmax policy for this task because the action space is discrete. Later on, we'll use a different parameterization for a continuous action variant of the pendulum task. The next step is to find the reward function. The goal is to get the pendulum pointing directly up and keep it that way. So the reward is equal to the negative absolute angle from vertical. If the pendulum reaches a large angular velocity, then it could damage the system. That would be bad. To avoid this, we constrain the range of the angular velocity to between minus 2 pi and 2 pi. If this limit is exceeded, then we reset the pendulum to the resting position. The goal is to keep the pendulum as close to upright as possible at all times. This continues indefinitely. There are no episodes and no terminations. So it makes sense to formulate this as a continuing task. The pendulum is interesting for a few reasons. The actions are not strong enough to move the pendulum directly to the vertical position from the resting position. A good policy must apply actions that move the pendulum away from the desired position in order to gain enough momentum to swing up. Finally, the vertical position is unstable, so a good policy must continually balance the pole. Let's apply our softmax actor-critic algorithm to our simulated version of the pendulum task. Before we can do that, we have to design our function approximator and our policy parameterization. The pendulum task has a low-dimensional state, just the angle and angular velocity. this two-dimensional problem is a good fit for tile coding. The approximate value function and the action preferences will be linear in the tile coding, but nonlinear in the state variables. The first step in setting up a tile coding is to figure out the range of each of the state variables. This is easy for the angular position. It just has to be between pi and minus pi. The angular velocity will lie between 2 pi and minus 2 pi due to the constraint we discussed earlier. It is usually good to use large tiles and many tilings. The broad tiles enable considerable generalization and thus fast early learning, while many tilings help with discrimination. This should result in an accurate approximation of the value function and the action preferences. We use 32 tilings of size 8 by 8. Remember, for our action preferences, we need a feature vector for each state action pair. As before, we simply use a separate copy of the state features for each action. What about the step sizes for the average reward, the actor, and the critic? That's quite a few parameters, and each of them have a big impact on performance. We performed a systematic sweep to determine a good setting for each. This matches the general rhythm that we want the critic to update at a faster rate. That way the critic can accurately critique the more slowly changing policy. There are a few other details required to get good performance on this task. For the sake of time, we will skip those, but don't worry. You'll learn all about this implementation in your assessment. Let's look at a video of the agent as it first begins interacting with the pendulum environment. The agent begins by acting randomly, but it quickly learns to add energy to reach states closer to vertical. Let's skip ahead a bit. The final behavior looks something like this. We added random perturbations to demonstrate the robustness of the learned policy. This is like flicking the pendulum with your finger every once in a while. The perturbations were introduced only after the agent had learned a good balancing policy. The perturbations are shown with black arrows in the video. We can see how the trained agent is able to recover smoothly and is robust to these flicks. It's really satisfying to watch an agent we programmed mastering the pendulum problem, but we have to be skeptical scientists too. This is just a demonstration. Does the agent successfully learn to balance every time, or did we just get lucky? How quickly and robustly does it learn? To answer these questions, we ran the experiment 100 times and averaged the performance. To measure the performance of the agent, let's plot an exponentially weighted average of the reward over all time steps. The error bars show the standard error and the mean. The error bars are quite small. In fact, the error bars are so small you can hardly see them at all. So we are pretty confident this plot accurately reflects our agent's average performance on this task with the parameters we have chosen. The average reward starts off low, but increases very quickly off the start. After a short time, the rate of improvement slows, but improvement continues as the agent continues to refine its policy. Performance peaks near zero. This means the agent is generally able to balance the pendulum upright with minor deviations. Then it stays steady from that point forward. That's it for today. We introduced a specific implementation of an actor-critic learning system, and we tested on a classic control task. Bye for now.
One of the nice things about policy-based methods is that they give us a natural way to deal with very large or even continuous action spaces. We don't have to use a policy parameterization that assigns individual probabilities to each action. We could instead learn the parameters of some distribution over actions. In this video, we will discuss how to learn a state-dependent Gaussian distribution over continuous actions. By the end of this video, you will be able to derive the actor-critic update for a Gaussian policy and apply average reward actor-critic with a Gaussian policy to a task with continuous actions. Let's look at the same pendulum swing-up task we explored last time. The state space and reward is exactly the same. This time, we will use a continuous interval for the action space instead of just 3 discrete levels of angular acceleration. The angular acceleration can be anywhere between -3 and +3, which are the minimum and maximum. We cannot assign a probability to every action separately because the space of possible actions is infinite. One solution is to restrict actions to a discrete subset of the full range of possibilities. This is what we did previously. In this case, we compromised by picking a set of actions that were gentle enough to allow fine-grained control. But this also inhibits the agent's ability to apply larger acceleration. We'd really like the agent to be able to apply large acceleration when it's appropriate and smaller acceleration to correct its balance. Towards this goal, another strategy is to parameterize the policy as a continuous distribution, such as a Gaussian distribution. A Gaussian random variable x has the probability density function shown here. Here are a few examples of this PDF with different means and variances. Note that the y-axis in this case is density and not probability. Probability density means that for a given range, the probability of x lying in that range will be the area under the probability density curve. The parameter mu controls the mean of the distribution. If mu is 0, the distribution will be centered around 0. For this curve, mu is -2, so the distribution is centered around -2. The parameter sigma is the standard deviation, the square root of the variance. If sigma is low, like this curve, the distribution will be sharply peaked around the mean value, mu. As sigma becomes larger, the distribution is more spread out, like this curve, and x is drawn from a wider range of values. Let's define our policy using a Gaussian over actions. We make the parameters mu and sigma functions of the state. This way, the agent can assign different action distributions to different states. Mu can be any parameterized function, but to keep things simple, let's make it a linear function of the state features. The policy parameters associated with mu are denoted by theta mu. The parameterized function sigma has one constraint. It must be positive. To enforce this, we will parameterize it as the exponential of a linear function. The policy parameters associated with sigma are denoted by theta sigma. Our policy parameters now consist of these two stacked parameter vectors of equal size. We've defined our Gaussian policy. Remember, the main point of a policy is that it gives us a way to select actions. To select actions with this policy, we sample from the Gaussian. Many programming libraries include functions to sample from Gaussians, so we won't worry about that here. The procedure is simple. In a state, we compute mu and sigma from that state. We then call the Gaussian random number generator with that mu and sigma. In one state, mu and sigma might look like this. For this state, a wide range of actions are likely to be sampled. Here's an action that might be sampled in this state. In another state, mu and sigma might look like this. For this state, only a narrow range of actions are likely to be sampled. Here's an action that might be sampled in this state. Sigma essentially controls the degree of exploration. We typically initialize the variance to be large so that a wide range of actions are tried. As learning progresses, we expect the variance to shrink and the policy to concentrate around the best action in each state. Like many parameterized policies, the agent can reduce the amount of exploration over time through learning. Though we now have continuous actions instead of discrete actions, we can use the same actor-critic architecture. The algorithm is actually very similar. The main difference is that the gradient of the policy is different because the parameterization is different. Underneath, the objective also looks slightly different because we integrate over actions instead of summing. But sampling the gradient ends up being the same. So all we have to do is work out the gradient of the natural log of the policy. We'll skip the steps here, but the result is shown on the slide. As an exercise, try to verify it for yourself. So, we now have an update rule for continuous actions. But why did we do all this given that the discrete action set we used previously seemed to work fine on this problem? The most obvious reason is it might not be straightforward to choose a discrete set of actions. For example, imagine a robot trained to play golf. Putting accurately requires quite a bit of precision. We could try to pick a discrete set of forces to apply to the club and hope it's good enough, but inevitably there will be situations where it isn't. Depending on the distance and terrain, we may need to use the full range of forces. Continuous actions also allow us to generalize over actions. For example, the Gaussian policy smoothly assigns probability density to nearby actions. Imagine an action is found to be good, and the update increases density for that action. The density for a nearby action will also increase, with the agent generalizing that those actions are likely also to be good. Finally, even if the true action set is discrete but very large, it might be better to treat them as a continuous range. This gives a natural way to generalize over them and avoids the costly process of exploring each one independently. Now let's see how this actor-critic algorithm performs on the pendulum swing-up task. Again, we swept over many step size values. We used separate step sizes for theta mu and theta sigma. Here we visualize the policy in early learning. It doesn't look too different from when we were using a discrete action set. It quickly learns to rock the pendulum back and forth. The size of the arrow around the pivot indicates the magnitude of the angular acceleration applied at a given time. Here, we visualize the policy at the end of learning. It's learning a very nice balancing policy. Here again, we added perturbations to highlight the robustness of the learned policy. And that's it for today. You should now understand how we can apply actor-critic to problems with continuous actions, and we showed an example of how this can be done with the Gaussian policy parameterization in a simple environment. Bye for now. This week, we talked about a whole new way to do control, directly learning parameterized policies. We introduced a new objective and a new algorithmic framework called actor-critic. Let's take a step back and look at where this new material fits into the bigger picture. We learned policies using function approximation, so we're still on the left side of the map. We focused on actor-critic using the average reward objective, so that puts us here. From there, we introduced two possible parameterizations depending on whether the actions are continuous or discrete. For discrete actions, we use the softmax policy parameterization. For continuous action spaces, we used a Gaussian policy which samples actions from a continuous range. This is the first time we implemented an algorithm for continuous actions. Average reward actor-critic can be used in the same settings as the differential semi-gradient Starsa algorithm we introduced previously. We started this week by making the shift from parameterized action values to parameterized policies. Parameterized policies take in state action pairs and output the associated action probabilities. This function is parameterized by a vector of parameters denoted by theta. A parameterized policy has to be a valid probability distribution. That is, every action probability must be greater than 0, and the sum over all actions in a given state must be 1. A softmax over action preferences is one way to ensure the parameterized policy obeys these constraints in discrete action spaces. Parameterizing policies directly has a number of potential advantages. These advantages include the ability to autonomously converge to a deterministic policy over time, while using a stochastic policy to explore early on. Another advantage is the ability to learn stochastic policies. This can be useful with function approximation when the optimal deterministic policy is not representable. And finally, we discussed that a good policy might be easier to learn and represent than precise action values. To learn parameterized policies, we had to consider a new objective and a new strategy to optimize it. We revisited the average reward objective. We showed that the average reward could be expanded out like this. Our strategy to optimize this objective was to use stochastic gradient descent. For that, we needed an estimate of the gradient of the average reward. This is challenging because the state distribution mu depends on the policy parameters. The policy gradient theorem provides an expression for the gradient of the average reward objective that's convenient to optimize. This form allows us to estimate the gradient by sampling states from u by following the policy pi. Using the policy gradient theorem, we derive the actor-critic algorithm. Actor-critic simultaneously learns a parameterized policy, the actor, and an estimate of the policy's value function, the critic. The TD error from the critic reflects if the actor did better or worse than the critic expected. The actor is trained to favor actions that exceed the critic's expectations. The critic is trained to improve its value estimates of the actor so that it knows what value it should expect for this actor. We demonstrated how the actor-critic algorithm can be used for both discrete and continuous action spaces. For discrete actions, we used a softmax policy parameterization. For continuous actions, we used a Gaussian policy with state-dependent mean and variance. This made the Gaussian policy over actions conditional on the state. Now you know how to parameterize and learn policies directly. In addition to the action value methods we looked at before, This is a valuable new tool in your reinforcement learning toolbox. In Course 3, we showed you how to use reinforcement learning with function approximation. We covered how to approximate value functions and policies using neural networks and fixed basis approaches like tile coding. We discussed how function approximation allows for generalization, which helps the agent learn faster.
But we might lose some of the ability to discriminate between the values of states. The function approximator may no longer be able to get all the values right.
The agent then has to decide how to balance accuracy across states, how to allocate its limited approximation resources. We introduce objective functions to specify how to balance approximation error and discuss gradient-based algorithms to optimize those objectives.
Using all this new knowledge, you are ready to implement a complete reinforcement learning system. You will study a problem that highlights some of the challenges you might face when applying RL in the wild.
In Course 4, you will be putting together your knowledge from Courses 1, 2, and 3 to land a lunar module on the moon. When Adam and I start working on a new problem, we start by having meetings to brainstorm about how to best frame the problem and gather ideas about potential solutions. There's rarely one right solution. Throughout, we will reason with you how we might approach designing an agent for this problem.
We will start by discussing how to formalize the problem as an MVP. If someone just told you, design an agent to land this lunar module, you would have to figure out how to turn that goal into a problem formulation. So that, of course, is where we begin.
Then we'll think about how to choose an appropriate learning algorithm. An important part of this is actually thinking about all the details of the algorithms involved. This includes determining how the agent explores, the type of function approximation architecture, details inside the function approximator such as the number of features it produces, and the list goes on.
A big part of this course is understanding the importance of all these details and how to try to gain some insight into how your algorithm behaves with different choices. Practical implementation begins with understanding.
So, let's not just sit here talking about it, let's dive right in and get our hands dirty.
With moon dirt, of course.